And of the many techniques that we are talking here, we will be talking about XPS, a little about Auger electron spectroscopy, because that is something which is coexistent in X-ray photoelectron spectroscopy. Well, other techniques which I have mentioned in this slide, like IR, UV-Vis, ESR, NMR, Raman, and all, SEMTEM, the other participants have already talked about those in detail. So today I am talking about X-ray photoelectron spectroscopy. Before going to the technique as such, I'm trying to let you understand that these are some of the techniques that I have used in the institute. This is the thermal analysis techniques. We had both these instruments by thermal thing. This is a DSC, which can go from -90 to 725 degrees centigrade. Versatile instrument with an auto sampler. But anything, as you all know, whenever we approach a technique, the first thing, important thing that we should know is to let us know the conditions under which these samples have to be analyzed. So for both the TGA or DSC, the conditions that are needed are the heating range in which the experiment has to be done, the heating rate at which the sample has to be programmed. That is a program. It can be dynamic or isothermal. So whatever may be your conditions, you have to let them know the heating rate. And another most important thing is the atmosphere in which the analysis has to be done, because people use purge gas, nitrogen as the inert gas, but that is not itself enough. If it is a reactive gas that needs to be used for our analysis, it becomes very important for us to let them know about that also. This one is the TGA. The only thing is this can go from room temperature to about 1500 degrees centigrade, and it is coupled to mass. So where you can the evolved gases that are coming out of this furnace are analyzed by passing them through this mass analyzer, and in this mass you can know up to 300 atomic mass units. So it gives us a complete idea about the sample, its decomposition pattern, that is the decomposition profile, the various steps that are there in the decomposition, and why those decomposition steps are coming out, because of the components that are coming out from the sample. So this is one technique that I have worked on. This is the particle size analyzer, Master Sizer 2000. Well, this was another very good instrument that we bought around 97. Where you can measure the particle size from about 20 nanometers to 2000 microns. This is based on laser diffraction technique. So you have a laser and laser beam falls on the sample. The sample goes through. This is the wet sample. This is the dry sample. So the sample goes through this cavity here, and when it goes through the cavity, laser light falls on it, and depending on the size of the particle, you get the distribution. Smaller, as you all know, smaller the particle, larger is the diffraction, and larger the particle, smaller is the diffraction. So taking that into consideration, it gives us a distribution profile. And it also helps us to know the only limitation here is that you have to 1 minute. Yeah, I'll put the video on so that you people can see me. Yeah, the only limitation here is that it takes whatever may be the shape of the particle, it takes it as a sphere. For example, if you have a rod of this length, it takes as two different samples and a thickness of something about few microns. It takes length as one sample and width as another sample. So which means that it takes a sphere as a standard one. So that is the limitation, but whatever it is a very good technique where the samples can be dispersed in various solvents. So here again, these are the conditions that are important. You have to know the dispersant name in which the sample has to be dispersed, the refractive index of that, and particle size of the sample name is there, refractive index of the particle, and the particle absorption are some parameters that we need to give. So dry sample is here. You have a vacuum pump on the other side, and this dry sample as such is sent through the cavity by sucking from the vacuum pump here. So both the techniques are useful, and most of the times both of them give uniform homogeneous kind of a distribution. But whatever it is, depending on the sample, we have to choose the appropriate standard operating procedures and try to work on. Okay, this is another one that I have put my hands on. This is the Shimadzu EDX 8100 energy dispersive X-ray fluorescence spectrometer. As you all know, X-ray fluorescence are both energy dispersive and wavelength dispersive. Though wavelength dispersive is more sensitive, but energy dispersive gives us a rough idea about the elements that are present in the sample. And this is a very small, cute, instrument of about the size of a rice cooker, or maybe a little bigger than that. And this is how it goes. Like, you have the X-ray tube. Various filters are there. These are the collimeters where you can change the size from about 1 millimeter to 10 millimeters. Yeah, and the sample is here, and it is the detector, and you get the information about the elements that are present on the sample. This one is like, you can have a, this can be done in normal conditions, room atmosphere, or you can bring the vacuum, do it in vacuum conditions. And there is one still advanced instrument, EDX 8200, where you can even use helium as the the atmosphere in which the analysis can be done. So each the experimental condition, as you all know, is a very sensitive parameter, and it helps us get better better properties or better chemical composition of this sample, as we try to do it in better atmospheres. So well, there are limitations. So this is a technique which can be used, as you can see here. Various applications are there. Only thing is, first-hand information without much difficulty, you can get to know the elements present on the sample. This is another one that I started to work on, a transshipment electron microscope, a 120 kV one, Techni FE12. After that, we got this new one, which is the latest one that we have. I will talk about this later. Well, this is the one, it gave a lot of satisfaction for having learned this technique. But later, we tried to work on this Talos F200X. It's a complete package in itself, because it's a completely automated, software-driven technique where you can know the do the TEM, high resolution, HEDAF. You can do the mapping. You can do line profiling. You can do point scanning, whatnot. Everything is there in this. Another very good technique. EDS is of course there, and it is something gives a lot of satisfaction when you try to put your sample in and try to get all kinds of data and try to get a good understanding of the material that you have synthesized, and it gives a wonderful image of whatever we have done. Now, coming back to the technique which my interest is all about in today's talk, electron spectroscopy for chemical analysis, ESCA. This is another name for XPS. So it's also called XPS, that is X-ray photoelectron spectroscopy, more frequently called as XPS, but it was earlier called as electron spectroscopy for chemical analysis, and both mean the same. So we will try to understand about this technique. I will try to let you know what are the various things that are there on the instrument. You can see it's a complex one. So there are the source, the detector, all these things are there on here. I will try to explain one after the other and their importance. And I will try to give you some few spectra and try to make you people know how we try to do the analysis and try to understand the various features that are there in the spectrum. This is the new one that we have now. This is the Kratis Access Supra Plus XPS. Well, the earlier model was mostly manual, but this one is all automatic, and the software, everything is automatic. Only thing is you'll have to place the sample in somewhere here. Once the sample is loaded into your instrument, then rest of it is all driven by software. And it's another very good instrument which has given us a lot of sensitivity and resolution on very sensitive samples, and we could get a lot of valuable information. And the other thing that about this particular instrument is that it has various other techniques that are, that can be, attached to the same instrument. Because you see, the whole hardware basically looks almost the same. The vacuum conditions, everything looks the same. Only thing is the probes that you try to put on the sample, and the detectors, that appropriate detectors that are there on the other side of the sample, are the ones which make all the difference. So these are some techniques that can be done, like Auger electron spectroscopy, SAM, SEM, ultraviolet. This is UPS. I will talk about a little about this, because this is also a small part of XPS, and ion scattering spectroscopy or secondary SIMS and all. So these are some, techniques, secondary techniques that can be put onto the primary instrument, and you can get the data from XPS and also correlate the data from, these techniques, and try to understand about more about the sample, and give us a better idea. As I told, this is driven by, ESCAPE software, with analysis like MEM software and all for, angle resolved XPS. I'll talk a little about this in my later talk, and we'll try to understand these things. Now, this is an excellent review by Professor Kazuhisa Miyoshi on surface characterization techniques. So most of the time, people thought that it is the bulk that is the one which makes all the difference in with the properties. Let it be magnetic, let it be electronic, let it be various other properties. So, but it was felt that it was the bulk that makes all the difference. But later, when people try to understand the materials and their chemistry better, people have tried to understand that it is mostly the surface, or the first few layers of the surface of the sample are the ones which make the difference when we are trying to look at various changes in the properties which are more significant when compared to the bulk of the material. People who want to use, you know about this, this particular slide, maybe you can refer to this article by Professor Mayushi and try to know. So these are very common things. People all know that bulk, interface, thin films, surface analysis, and the various depths that are there. And mostly the surface is contaminated in our conditions. But when we try to use sophisticated techniques, people try to remove the contaminant and try to know the properties of the material better after the surface contamination. Well, this is a slide which everybody shows, especially when people talk about any radiation interacting with matter. So this is a very commonly used slide. So you can, as can be seen in the slide, various interactions with the sample of the incident beam, depending on the appropriate detectors, you can try to know the properties as is of interest. So it can be, like the plasmon excitation, X-rays, Auger, secondary, backscattered. So, but each is a technique in itself. So you can have this inelastic scattered electrons. And of course, the direct beam that we are talking about here, if you have an electron beam here, and the transmission electrons microscopy is something which we are talking about. So, okay. When this radiation, in the earlier slide, what we told about the radiation falling on the matter. So when such radiation falls on matter, various things happen inside the sample, and that too mostly on the surface. The surface ones are, mostly elastic, where, they will, without losing their energy, they are coming out of the surface, and depending on the conditions that are there, you have some things like this. But inside the sample, there are so many things that are happening, and depending on the energy that is there, which is, if it is sufficient for them to leave the sample surface and go into the vacuum and to the detector, you can detect them. Or else, mostly they tend to be in the sample and try to generate, such secondary events like thermal heat or, such kind of things. So these are some things that are happening, which are, complex things that are there, which we try to understand. So when we talk about spectroscopy or microscopy, well, there can be only three inputs. It can be either an electron beam or a photon or an ion beam. So these inputs, when they are falling onto the sample, the outputs that are coming are also the same similar radiation, either with less energy or little more. You can, like in electrons, photons, and ions. So if you are looking about electrons as input source, that is the probe, when it falls onto the sample, two possibilities are there, either the electrons that are coming out or photons that are coming out of the sample, and each give us valuable information. As can be seen here, from for example, if you are looking at secondary electron imaging or backscattered imaging or transmitted electrons or electron diffraction, you are looking at electrons that are coming out of the sample, origin electron as well. And the photons, as I talked about in my earlier XRF, so energy dispersive spectroscopy or wavelength dispersive spectroscopy are the spectroscopies that you are from that you get the information from the photon that is coming out of the sample. These are very common things that normally people all know. When photon, that is light, or light which is visible infrared or IR or FTIR and all. So these are techniques that use light as the source, that is the photon, and the photon that is coming out of the sample with lesser energy or little more gives us information from all these kind of spectroscopies like FTIR, Raman, visible, UV, X-ray fluorescence, and diffraction, and so on. Our interest here is on electron spectroscopy, photoelectron spectroscopy, where you have a photon that is falling onto the sample, which can be X-rays or ultraviolet rays or so on. So these X-rays, when they fall onto the sample, photoelectron is ejected. This photoelectron gives us valuable information about the sample. We will try to understand this in detail in my future slides. Well, if it's ion as a source, you have these kind of spectroscopies like SIMS, time of flight SIMS, ICP-MS, and so on. So in all these techniques, the ones which we are going to talk about, there are so many different techniques that use X-rays as a probe. So here we have energy dispersive, wavelength dispersive, X-ray fluorescence, XPS, X-ray diffraction, and so on. So in all these techniques, the source is X-rays. Now, there are two things that I have to talk about before we go into the depth of the technique. That is the depth resolution and the spatial resolution. Depth resolution is the depth from which we are getting the information. Spatial is the surface area from which we are getting the resolution. There are so many different techniques here, but as you can see here, Auger, SIMS, XPS or ESCA, imaging, which can be imaging or chemical composition. All these are, the depth from which you are getting the information is hardly 10 nanometers, which means that the spatial resolution is okay, but the depth resolution is very less. On the other hand, XRF and XRD are bulk techniques where you can get information from about 10 microns or so. So what I mean to say is that the imaging or XPS or imaging XPS or ESCA or these are surface sensitive techniques because the information that you are getting is from the top few layers of about 10 nanometers of the sample. So this is the same thing in a different slide. You can see the top surface and the very few techniques that can look at the top surface and give us information. Near surface and thin films, coatings, and bulk substrates. So XRD and XRF are the only two techniques that are giving us from bulk substrates. But our interest when you're talking about XPS or Auger electron spectroscopy is from the near surface of about 10 nanometers. So well, I've talked about it in my earlier slides. So what's so special about the surface of the materials? Well, all of you know, when you are talking about supported catalysis or in heterogeneous catalysis, it is the surface that plays a major role in the catalytic activity, where because the active species that is present on the surface is the one which undergoes redox cycle during the catalytic process, and at various stages you can look at the changes in the catalyst and try to give a concrete evidence of the mechanism that is taking place during the catalytic activity. For such studies, this XPS is one beautiful technique which can be used. Well, if you are looking at surface addition by coating, paints, adhesives, and all, where you, for example, in corrosion, because of the environment, like Chennai, as you all know, you are all along the sea coast, which means that most of the materials get easily corroded because of the atmosphere that your people are living in due to the coastal atmosphere. So these kind of surface corrosion studies are also studied by using XPS, and in many biological materials and so on. So, so these are like, so these are another representation. We are talking about bulk, where you can, the bulk material, their properties are mainly controlled by physical properties like density, strength, flexibility, etc. Whereas surface typically controls chemical interaction with other materials and environment. So this is, for example, if you are looking at the surface, the interface also plays a little role in the properties of the material. Most of the times, it is the semiconducting materials which are widely studied by XPS because the various properties, electrical properties, and the multi-layer coatings that are there in these kind of materials give valuable information about these kind of materials. Okay. Well, some of the greats who have worked on X-ray XPS and before that X-ray as such, because that is the source of the instrument. So people who like the Hertz and Rodington are the people who have done on X-ray diffraction. But it was photoelectric effect that was first studied by Einstein, explained by him, for which he got Nobel Prize in the year 1921, which forms the basis of this particular technique. And that was developed by Professor Segbin of Uppsala University. And he was the one who tried to develop this photoemission or photoelectron spectroscopy as an analytical tool and try to understand this, for which he got Nobel Prize in the year 1981. So which shows the importance of this material, the basic of photoelectric effect. When light falls on the sample at its threshold, electrons are ejected, and these ejected electrons are what are called photoelectrons. This basic principle of science could be developed into an analytical tool, and it was so important that it was recognized and he was awarded Nobel Prize. And here you see Professor Segbin. He is the father of Professor K. Segbin. He was also a professor and he worked on X-ray diffraction, for which he got Nobel Prize. And it seems that Professor K. Segbin, son of Professor Segbin, occupied the same chair in the same university after his father. And he was so, he also got Nobel Prize, which shows that a father-son relationship getting a Nobel Prize in this particular kind of work. Okay, there are various modes. Before I go to the actual technique, let us try to understand briefly how these, these are all possible by X-ray, X-ray photoelectron spectroscopy. Well, first thing is to know about the spectrum. So you have a spectrum here, and which can be done by both wide scan or narrow scan. I will talk about each one of them in detail when in my future slides. So the spectrum can be recorded as wide scan and narrow scan. Wide scan gives us information on quantification. Narrow scan gives us what are the information that we get from narrow scan is like quantification or components, whatever. I will try to explain all this. It can be used for imaging, where you can get line scan, map scan, you can stitch images, and if this image is a larger dimension, you can measure smaller dimensions and try to stitch each one of them and get an information about larger area. You can do a spot analysis as well. And there are two other techniques called angle resolved and depth profiling. So the angle resolved is a non-destructive technique, whereas depth profiling is a destructive technique, where we try to study the properties of the material in the bulk. So these are the various modes in which this technique can be done. I will try to explain some of them in detail. Okay. So as I told, I will give you some basics. I will let you know what is quantification, what are resolutions, electric energy resolution, count rates, wide scan, narrow scan, chemical state analysis, sensitivity, sputter depth profiling, line scan images, and mapping. These are some things I will try to talk about. Now, what is that information that we can get from XPS? XPS works by irradiating a sample material with monoenergetic soft X-rays, causing electrons to be ejected, and these ejected electrons are what are called photoelectrons. The identification of the elements in the sample can be made directly from the kinetic energies of these ejected electrons. So as these photoelectrons are coming out, they have some kinetic energy, and that gives us an idea about the elements that are present in the sample. The relative concentration of the elements can be determined by the intensities of the photoelectron peaks. So here we are trying to understand the elements that are present in the sample and knowing their concentration by knowing the concentration from the intensity of the peak of the X-ray photoelectron spectroscopy peak. So we will try to understand in detail. So I have already talked about this slide in the beginning, because when radiation falls, so many things happen here. But these things can be envisaged as 3 steps. The photoemission process can, though there are so many complex things that are happening in the sample, can be narrowed down into 3 steps. First is absorption and ionization, which is the initial state. Because of this ionization, you are getting the electrons that are coming out of the sample into the vacuum as photoelectrons. Then finally, you have some response from atoms and creation of photoelectrons. That is because of what is happening in the insect. And the energies of these things are less when compared to the initial state effect. And finally, it is the transport of electrons to the surface and escape, that is the eccentric loss to the vacuum. So the 3 processes can be narrowed down as absorption and ionization, response of the atom and creation of the photoelectron, and transportation of the electron to the surface and is into the vacuum. These are 3 steps that are very important. And as I've told you here, the deeper ejected electrons, see, these can be, the interaction can be elastic or inelastic. Elastic, there will be no loss in energies, but in inelastic, there will be a loss in energy. So the deeper ejected electrons, they are generally recaptured or trapped in the solid. Hello? Hello?
Yes, sir.
I'm audible, right?
Now audible, sir.
Why in between there was a problem?
I don't know, sir. There was some error, I think.
Oh, really? From which slide?
No, it's same, sir. I can start again from this slide.
From here itself. Okay, fine. No problem.
Yes.
No problem. Okay, thank you. Thank you. Yeah. So, as I've already told you, that X-ray photoelectron spectroscopy is a surface-sensitive technique, and these X-rays can penetrate to a depth of about 1 micron. And the information that you get from this technique is from the first few layers of the sample of about 10 nanometers, and the area is about 1 millimeter square. So this is the reason it is called a surface-sensitive technique. Now, the depth from which we get the fraction of the fraction of the signal that gives us the from the various depths that the number of photoelectrons that are coming out can be understood from this equation. This is the Beer-Lambert's equation itself. So where you can see, for example, from the depth of about lambda, this is the inelastic free path, you can get about 0.3% of the signal of the information from the sample. As you go deeper into the sample, 2 lambda and 3 lambda, and it is at this depth, that is 3 lambda, you get the maximum fraction, that is about 0.95% of the information from the sample. So if lambda is the inelastic free path, the depth, the maximum depth from which you get information from the sample is 3 lambda, and that fraction is about the 0.95%. That is 95% of the information. It is 95% of the information that you get from a depth of about 3 lambda when the theta, that is the angle at on which the sample is getting irradiated, is theta is equal to 0. Now, there are so many different, excitation energies, and this sampling depth as a function of exciting energy can be understood from this slide. So these are different techniques like ultraviolet photoelectron spectroscopy, X-ray photoelectron spectroscopy, and these are hard X-ray photoemission spectroscopy. This is another thing that is coming up recently, and our new technique has this one where you can irradiate the sample with silver L alpha, and you can go to a depth of about 18 nanometers. So depending on the source, like if it is a silver alpha, L alpha, or chromium or gallium, you can go deeper into the sample and try to get information. But our interest is mostly on X-ray photoelectron spectroscopy, which is from the depth of about 10 nanometers. In between, I will try to tell about these things also, so that you can get an idea, and maybe if you're interested, you can know about that in detail later. Yeah. So first thing, I told you that it is a surface sensitive technique. Now, the other very important thing is this is an ultra high vacuum system. Ultra high vacuum system because the sample analysis is done at the vacuum of the order of about 10 to the power of minus 11 torr. So this is the pressure at which this work is carried out. So that is the reason it is called ultra high vacuum technique. And this kind of pressure vacuum is created when cascading of three different pumps. One is the turbomolecular, this is a rotary pump, followed by a turbomolecular pump, and followed by an ion pump. So with these three different pumps working in tandem, you can create a vacuum of the order of 10 to the power of minus 8 to 10 to the power of minus 11, in which the sample is analyzed. Why do we need this kind of vacuum? The vacuum, of course, can help us remove absorbed gases from the sample, eliminate absorption of contaminants on the surface. Because we are working at a high voltage you can the arcing is prevented. And most important thing is to increase the mean free path of electrons, ions, or photons, depending on the technique that we are doing the analysis. So as you all know, because if the vacuum is not there, due to the contamination in the column, these photoelectrons that are ejected from the sample surface, due to their Brownian motion, they lose their energy in between before actually reaching to the detector, and they lose their energy and fall back onto the sample. So in order to increase this mean free path, such kind of vacuum is necessary. And the development of the technique, though the basic the photoelectron spectro effect was understood in the year 1921, it took about 60 years for developing this technique because this vacuum system, vacuum technology was not very well developed. And this is the reason it took for such techniques to be developed into. And that is one particular reason. And most of these vacuum techniques are done at very high vacuum. And these are some pumps that are normally used. Okay. This is a simple thing that all of you know, nucleus surrounded by electrons, and depending on the position from which these electrons are ejected, they have different binding energies. Valence electrons, which are far away from this nucleus, have low binding energy, whereas the core electrons, which are close to the nucleus, have high binding energy. So depending on the position from which these electrons are ejected, they have different binding energies. So this is the thing that we are trying to understand. We are trying to irradiate the sample with the X-rays, and these core level electrons are rated as photoelectrons. Okay. But there are two things that happen simultaneously in this technique. One is the creation of a photoelectron. As you have seen, radiation falls on the sample. Core electron is ejected as photoelectrons. And as this energy system is unstable, so electrons from higher levels relax. They also give out some energy. And these energies are taken by higher level electrons. And this electron is different, which is called an Auger electron. So these two events, that is creation of a photoelectron and creation of an Auger electron, happens simultaneously in this technique. So that is the reason that, when you talk about the analysis, you will understand that, these both the peaks due to these two electrons are normally present in the spectrum. So in photo XPS, both these events, that is the creation of a photoelectron and creation of an Auger electron, happens simultaneously. Okay, this is another thing which all of you are also familiar. That is the anion. Is larger in size than when compared to its atom, because it has gained an electron. So the cloud around, if you look at the electron cloud around the anion, it is larger when compared to the atom itself. On the other hand, if it's a cation, because it loses an electron, so it shrinks. The cloud shrinks in the case of a cation. So that is the positive ion is smaller when compared to its atom. So these are things that are that you all know. Only thing is, this forms a basis for you to understand the shift in the peak positions that you see in XPS. So for that reason, I am showing these things before so that you can understand that better. Okay. Now, if you look at this energy level diagram, there are two things. X-rays, you can knock the core electrons, or you can knock the valence electrons. So if you are looking at the core, getting information from the core electrons, this is what is called X-ray photoelectron spectroscopy. And if you are knocking the valence electrons by using ultraviolet rays here, I will let you know about the energies in my later slides. If you are using an ultraviolet rays here, to knock the valence electrons, you have what is called UPS, that is ultraviolet photoelectron spectroscopy. So depending on the position, the core levels or the valence electrons, you're getting different different information. But this is UPS and this is XPS. Okay, the basic principle on which this technique revolves is very simple. The kinetic energy with which these photoelectrons are coming out of the sample is nothing but the energy that you have given minus the binding energy. This binding energy, as I told, depends upon the position from which these electrons are ejected as photoelectrons minus work function, which is phi. This work function is something to do with the spectrometer, which is, that is actually during calibration, we do that and try to fix that work function. So the basic principle is very simple. The kinetic energy with which these electrons are coming out is nothing but the energy that you have given minus the binding energy, because this depends upon the position from which these electrons are ejected. Okay, I've told you that it's a surface sensitive technique, and that is the reason we get information from the first few layers of 5 to 10 nanometers. And these are some things that we try to understand here. We can identify all the elements except hydrogen and helium that are present in concentrations greater than 0.1 atomic percent, because it's a bulk technique. It's a surface technique. We are not getting information from the bulk. And that is the reason the information is semi-quantitative with a plus or minus 5% error. Most important thing is not only identification of the elements, which can be done by various techniques. As you all know, there are various other techniques like atomic absorption spectroscopy, ICP, ICP-ES or AES or so on. There are so many different techniques that can give us the idea about the elements that are present in the sample. But this technique, there should be something different. And that difference is we can know about the molecular environment. By knowing about the talking about molecular environment, I mean it is oxidation states and bonding atoms. I will try to explain about this. This is something unique about this technique, where we are trying to know the elements, their concentration, and their molecular environment, in which we are trying to know about their oxidation state and their bonding atoms. Surface sensitivity, we can measure both conducting and insulating materials. Insulating materials have some limitation because when X-rays fall on the sample, surface charge is developed on the insulating materials. So this charge has to be removed, for which we use what is called a charge neutralizer, that I will also talk about later. And variations in sample composition we can use by both the non-destructive and destructive elemental analysis, and try to know about the technique. So let us slowly go into the technique now. Okay, the source, the heart of the instrument is the X-ray gun. Normally, the systems have a dual anode X-ray source, and the two materials commonly used are magnesium K alpha and aluminum K alpha. The anode looks something like this. This is the from which these X-rays are actually ejected onto the sample. This is the sample on which the sample is there. You can see here. So X-rays fall onto the sample here. Okay, and the energies are, for magnesium K alpha, the energy is 1253.6 electron volts, and for aluminum K alpha, it is 1486.6 electron volts. With these two energy sources, most of the elements that are there in the periodic table can be analyzed, of course, except hydrogen and helium. And these days, though, people are coming with various other techniques, whether other sources, it is depending on the developing of the source. So there is an water outlet and water inlet to cool the anode assembly here. And on one side, you have, this has two surfaces. On one side, you have magnesium K alpha, and the other side, you have aluminum K alpha. So that is how it is there. And another very important thing is having, these are, of course, once you have the X-rays, then it can be either monochromated or non-monochromated. But as you all know, monochromated has advantage, where you can get better resolution and sensitivity, because same sample when you are doing with a non-monochromated magnesium anode, you see the full width at half max is broader, which means that this peak is getting overlapped here. So these instruments are either with a monochromator or without a monochromator, but most of the times it's better to have a monochromator, chromated X-ray source, so that you can get better sensitivity and this kind of resolution in the peaks that are there. This is the monochromator that I was talking about. You have a monochromator signal here. So X-rays go through this, and after they're getting the beam, it eliminates the satellite peaks that are there, and this is sent on to the sample. This radiation has a decrease in the full width at half marks of the line. So which means that you can get sensitivities like this. So for example, if you can see here in this particular spectrum, these X-ray satellite peaks, which are there in a non-monochromated source, are removed in a monochromated X-ray radiation. So it is this is a kind of thing that it is gives a better resolution of the peaks that are of our interest. Okay, the schematic looks something like this. You have the X-ray source, your sample is here, and these are the ejected photoelectrons are going through the slit plate here. This is the inner and outer hemisphere analyzer, energy analyzer, and this is these are the detectors. The Axis 165, the earlier instrument had only 8-channel detectors, but right now this instrument has a better one. So here, these photoelectrons that are going through this hemisphere are an appropriate voltage is applied across it, and because of that, they are separated and in their energies, and they are appropriately detected. What is here is, we have a magnetic lens and electromagnetic lens on either sides of the column, which helps these ejected photoelectrons to be nicely followed onto the slit plate and onto the detector that you can see here. So these are various things that are there. This is a charge neutralizer that I was talking about in case of insulators, because when such a thing is there, this, the surface charge is developed when insulated sample are irradiated by X-rays, and this surface charge is generally removed by applying this kind of charge neutralizer. Yeah, this is, there are two different, as I told, this instrument can be, used in two different modes. One is the spectroscopic mode, and the other one is the imaging mode. As you can see here, this, depending on the hemisphere that you use, you can have either of these modes. So this is the one which is the inside one. You have the spectroscopic mode, the hemispherical spherical energy analyzer, and this is the one which we use in the imaging mode. So this is the monochromator that I was talking about. This is a 600 watt high power X-ray monochromator, and this comes as a in the instrument. It looks something like this. This is the electromagnetic lens under the sample, which increases the solid angle of collection, and which means that more photoelectrons that are coming out of the sample are directed onto the detector. This is also a characteristic feature of the Kratos systems, because they have the largest this hemispherical analyzer of about 165 millimeter mean radius, and which can be used for both spectroscopic as well as imaging mode. And this is the detector. It is a 128 channel high sensitivity delay line detector, DLD, and it's a multi-channel plates that are there on this thing. And whatever is there, this is getting amplified, and then you get water in the spectrum. This is a schematic where you can see that X-rays onto the monochromator, monochromated bead forms on the sample. You have the electromagnetic lens and the magnetic lens and electromagnetic lenses on either sides. And this, as I told you, your voltage is applied across this hemisphere, and depending on the energy, they are separated, and you get whatever you want. Now, coming to the source. Well, I told you that magnesium K alpha and aluminum K alpha are the materials that are used for as source materials for X-rays. So, though, as you can see here, there are so many different materials that can be used as X-ray source. Then why only magnesium and aluminum K alpha? So the main thing is that these, as you can see here, the energies are different, but what is something that we have to observe is their line width. The line widths, for example, say copper K alpha, the one which is used for X-ray diffraction, the energies are very high, but the line width is also equally high, like it's about 2.6 electron volts. But which means that peaks that are there in 2.6 electron volts are overlapped as one peak. So in order to have a resolution in this area, we should have smaller line widths, and that is what you see in magnesium K alpha and aluminum K alpha to be about 0.7 and 0.85 electron volts. So of all the elements that are here, that is the reason magnesium K alpha and aluminum K alpha are used as sources in these kind of radiations, and it gives us a because you can get highly resolved peaks when you are trying to do these kind of analysis. As I told you, this is a UPS where people use helium-1 or helium-2 discharge light rays, and their energies of about 21.2 electron volts. And these kind of energies are just enough for knocking the valence electrons in the sample. Okay, now slowly let us come to the spectral part of it, where we'll see a spectrum and try to analyze the various features that are there in the spectrum, so that you can know how we can do that. So it looks a complex thing because there are peaks. First, there are two things that are present, as I told. That is the creation of a photoelectron, simultaneous creation of a photoelectron and an Auger electron. So we have peaks due to core level lines, that is the XPS peaks and the Auger peaks. And other than this, we have so many other things that are there, peaks due to plasmon, shake-up, and other things. So I will try to tell about them in my talk, one after the another. So basically, there are 6 features. All the features that you observe in XPS spectrum can be tabulated or can be listed into 6 features, and we will try to look at each one of them and try to understand these. Our photoelectron peaks, that the ones which are of interest, which are elastically scattered, they are sharp peaks in the spectrum. Other peaks like multiplet splittings are there, which can also be seen. A broad structure is there due to the electrons from the deeper. That is, as I told, there is the background is having a broader kind of a feature. So this background is because of the inelastically scattered electrons, which have reduced kinetic energy. And there is the satellite peaks are there, which can be of 2 kinds. One is shake off and the other one is shake up. There are plasmon peaks, which are also there, which are of 2 different kinds of plasmons, and also the Auger peaks, because these are some things which are simultaneously present in the sample. Now, let us take one example and try to understand here. As I told you, that these stepped kind of feature that you are seeing is something very commonly observed in XPS. And this background is because of these inelastically scattered photoelectrons. So whenever you see an XPS spectrum, you will see that the background is having features that is a stepped kind of thing like this. Then our interest is to know about the photoelectron peaks, which are sharp. So these sharp ones which you see are due to the elements that are present in the sample. This spectrum is what is called a survey scan or a wide scan. This is what is called a survey scan or a wide scan. As the name suggests, with one go, you can know about all the elements that are present in the sample. In this particular sample, as you can see, the elements that are present are oxygen, carbon, and silicon. And these broad peaks that you see here are due to the Auger peaks, Auger electrons coming out of oxygen. So our interest is though not this, but they are inevitably there and in an XPS spectrum. Now, another thing is this carbon. Carbon is always present in a XPS spectrum unless like you have done some future from sample purification studies and so on. Otherwise, carbon is inadvertently present in this particular spectrum because of the oils that are present in the rotary pump. So rotary pumps have oils, and these oils are sometimes, they are in the vacuum that is there in the system. Because of that, you see that carbon 1s is always there, peak is always there in a XPS spectrum. But it is a blessing in disguise because this is the one which is used for calibrating this sample, this spectrum that we have obtained for that particular sample. Though the instrument is calibrated by using silver or gold as a standard, that is the NIST standard of gold or silver samples, but that cannot be done, that need not be done for each and every sample analysis. So in that case, what happens is this carbon 1s is the peak that is used for calibrating the sample, the spectrum that we have obtained for that particular sample. So this particular pattern or the spectrum that you are seeing is what is called a wide scan or a survey scan. Now, this is what is called a high resolution narrow scan. Our interest was to look at silicon, which was there in that particular wide scan. So the silicon was in the range of about few hundred nanometers. that particular peak, when it was recorded in high resolution, it was not a single peak, but it was having two different peaks. And these two different peaks are due to the elemental one and the oxide one, which means that this is silicon and this is silica. Okay. And this silica peak is around 104 electron volts. This silica elemental peak is around 99 electron volts, whereas this oxide peak is around 104 electron volts. By taking the area under the curve, we can quantify and know how much is silicon and how much is silica, depending on the peak intensity, full width at half max, and various other parameters, which we will talk later, and which will give us an idea about the concentration of these, this element in its oxide form and in elemental form. Okay, so this is high resolution narrow scan, and where we are trying to know. So in our survey scan, we came to know about the elements present in the sample. That is one thing, but that is itself not enough. We have to know something more, and which I told you as molecular environment. So in this case, the molecular environment is different because you have silicon in silicon, whereas in silica, it is oxygen. The neighboring element is oxygen. So silicon surrounding with oxygen. So the effect of this oxygen on the silicon is different. So that results in some change. And that change is what is observed as a shift. And this shift is what is called chemical shift. And this chemical shift is the one which helps us know about the elements, their oxidation state, and their molecular environment. We will try to understand that better. So this is the same thing. You have the electron. I told you in case of silicon. So you have a pure element where you have electron repulsion and electron nucleus on almost equal. But when you have another element that is coming next to it, depending on its properties, you will see a shift in their molecular environment. So this, as I told, is what is called a chemical shift. And this chemical shift is a small change in the binding energy of either core or valence, resulting in molecular environment, formal oxidation differences in lattice sites, and any that changes that electron density, any changes that are happening due to the neighboring element on the electron density around the atom of our interest is what is seen as chemical shift. So let us look how in case of silica, that is, as all of you know, silica is, you have silicon in a tetrahedron with 4 different oxygen atoms. And oxygen is electronegative, which means that when it is because of its electronegativity, it pulls the cloud towards it. So when it pulls the cloud towards it, what happens is the cloud around the element shrinks, and this cloud around the oxygen enlarges. So as it enlarges, the energy that is required to knock the valence electron is more in case of silicon, whereas silica, and less in case of oxygen, because this shrinks. So the energy required to knock the core electron increases. That is why you see a shift of about 5 electron volts when silicon is in the form of silica. That is one silicon, as I told you, it is 99 electron volts. But because of the electronegative effect of oxygen, that is the neighboring element to silicon, the cloud shrinks. That requires an extra amount of about 5 electron volts to knock the electrons out of it when it is in the form of silica. So this chemical shift is something very valuable in this technique, like in NMR and others, to give us valuable information about the molecular environment in which in this we are talking about oxygen. But depending on whatever be the neighboring element, you have the characteristic effects on the element of our interest, and that can give us valuable information. So these are some examples. Here we talked about oxygen as electronegative atom, and which shifts into higher binding energies. So depending on the neighboring element or the electronegativity, you can see a shift in their binding energies. Like for example here, for chlorine, it is in case of carbon, Carbon-carbon is normally taken as 285 or 284.6 electron volts, depending on its, whether it's amine or alcohol or chlorine or fluorine or oxygen, depending on that, the double bond here, you see a shift in the binding energies, and that gives us an idea about the molecular environment. Fluorine, most electronegative element in the periodic table. So that depending on the number of fluorine atoms also, it affects the binding energy peaks. For example, if you have 2 fluorine atoms or 3 fluorine atoms, you see a maximum shift of about 10 electron volts from carbon-carbon binding energy peaks around here, around 284.6. So if there are 3 fluorine atoms, you see this peak shifted to about 296 or 97 electron volts in case of when there are 3 fluorine atoms, because that is the max that electronegative, as you can see here, 293 to 297 electron volts when you have 3 fluorine atoms. So depending on the molecular environment, like it can be a singlet or doublet like this, and the number of oxygen atoms, these are all molecular effects that result in a chemical shift, and this shift gives us an idea about the molecular the atom and its neighboring atom, and how this neighboring atom influences the atom of our interest. Okay, let us take this example. That is the polyethylene tetraphthalate, where the molecular structure looks something like this, and the elements that are present are only carbon and oxygen. And this is the high-resolution narrow scan of carbon and that of oxygen. And this high-resolution narrow scan can be nicely deconvoluted into 3 different peaks. And these 3 peaks are characteristic of the environments here, that carbon-carbon, carbon single-bond oxygen, and carbon double-bond oxygen. So as there are 3 different kinds of carbons here, you can see that these peaks due to carbon-carbon, single-bond oxygen, and carbon double-bond oxygen. And you can quantify them, deconvolute and quantify them, and you can see that both experimental and theoretical values are pretty close. Similarly, oxygen is present in 2 different environments, single bond and double bond, and you can very clearly see that these peaks can be deconvoluted into 2, and area under the curve gives us something close to what is there in theoretical values. So, well, the routine things are already there, NMR and all things that gives us an idea about this. But when these materials are incorporated in inorganic materials, and you have some hybrid kind of materials where you have both components of inorganic and organic things together, and the presence of these materials in that inorganic composite or whatever you call them, that in such samples, it becomes very easy for us to characterize and know the presence of these elements in that kind of materials. Now let us come to little complicated thing where you are trying to see peaks due to splitting of peaks like here, like you can see here. In case of gold, you have 4d 3/2 and 4d 5/2, and these peaks are observed for p, d, and f orbitals. Where you have 2 peaks, and this is due to what is called spin orbit splitting. So the spin orbit splitting of core element is different compounds are nearly the same. So, and you can, depending on the peak area ratios, where it gives us an idea about the various components, because various elements, because those are all characteristic of the elements. Okay, so now all of you know about the quantum numbers, the principal quantum number, orbital angular quantum number, total angular quantum number, that is J, which is equal to L plus S, and S is the spin orbital momentum quantum number, which takes the values plus half and minus half. And the orbital angular momentum quantum number, depending on the orbitals, can take different, like for SPDF, it takes, for S it is 0, for L it is P is equal to 1, D is equal to, these are all things that we all know. The nomenclature goes something like this in the notations. Here you have the N value, the P is something you are getting from P, you are getting this L values, and this is what is given by J, which is equal to L plus or L minus S, L plus S and L minus S. So S can take either plus half or minus half. So you have 2 values for J. That is, in this case, it is 3/2 or 5/2. So depending on, for example, if this p orbital L is equal to 1. So J can take values half or minus 3 by 2 because S is like this. And the degeneracy is given by 2J plus 1, though it's not mentioned here, 2J plus 1, which gives us an idea about the ratios. That is, if you put 2J value plus 1 here, you will see that, because it is plus half and plus 3 by 2 here, the areas are in the ratio 1:2, which means that the spin orbit splitting that you are observing, these peaks are due to the P 3 by 2 and P half, and the area of these two peaks is in the ratio 1:2 when it is P orbital, where L is equal to 1. On the other hand, when you go for B, L is equal to 2. So your J value can be 3 by 2 or 5 by 2. And this degeneracy that is given by 2J plus 1 is 2. If you put that, you will see that the area ratios are 2:3. So it's not that any two peaks appearing as spin orbit splitting are the characteristic peaks of the elements. It is not like that. The characteristic peaks should be at the position. The area under the areas of them should be, the ratio, that is the area ratio should be 2:3, and the distance between them is also characteristic of the elements because of the degeneracy that you see in the electron configuration. So in F you have, when in F orbital, we have L is equal to 3. So you have two different values, 5 by 2 and 7 by 2. And here the ratio is 3:4. So we will try to take one example and try to understand this part of it clearly. So this is as I have told you, spin orbit splitting, peak ratios, L is coupling, J is equal to L plus or minus half. So this is the one which takes these values. And the area under the peak area ratios is given by the degeneracy 2J plus 1. So if you look at for carbon 1s, it is only 1 orbital, so you just don't have anything. So this is it. But in case of copper, it is p orbital, so L is equal to 1, S can take plus r of minus half, so J is equal to half and 3 by 2. So the two peaks that are you observing are due to 2p half and 2p 3 by 2. The distance between them is precisely 19.8 electron volts, and the area ratio is 1:2, which I told you get from the degeneracy, that is 2J plus 1. So similarly, silver, D, L is equal to 2. So J can take values 3 by 2 and 5 by 2, and that is what you see here. The area ratios is 2:3, and the distance between these two peaks is characteristic, and that is about 6 electron volts. Similarly, for gold, it is 4F. So F is L is equal to 3. So J can take values 5 by 2 and 7 by 2. These are the two elements that we normally use for calibrating the system. And this peak is around 283 point something. So the ratio, the distance between them is 3.65, and the ratio is about 3:4. So like that, these characteristic peaks that we observe from these elements are due to the spin orbit splitting, where you see two different peaks as spin orbit splitting. Now let us take a spectrum and try to unknown spectrum and try to understand. So it is but from the caption that is given here, you can know about our own work which we had done some time back. So it gives us an idea about the element, about the sample. So this spectra, this is a LDH, that is layered double hydroxides with the palladium as the active species. That is the catalyst that is used for Heck reaction with iodobenzene. So maybe all of you must be, I hope that you people know about this kind of chemistry. So we are talking about Heck reaction here, where layered double hydroxide with palladium as the active species is the catalyst that was used for this particular reaction. When we are talking about layered double hydroxides, well, all of you know these layered double hydroxides are magnesium hydroxide or magnesium aluminum hydroxide. They are in layers like this, with water molecules separating these layers, and you replace the magnesium with either aluminum, gallium, or so, and see a change and bring a change in their energy difference, the electron differences, and or like ions like nitrate, carbonate, and so on. and try to develop these kind of new materials as layer double hydroxides. And in this, which means that the elements that are present in layer double hydroxides are magnesium and aluminium. Palladium is one thing, and benzene, which is carbon, and iodo is because of iodine. So if you try to look at the various peaks that we have observed here, you can see peaks characteristic of magnesium, aluminium here, palladium here, carbon here, oxygen here, and iodine here. And this is, of course, the Auger peak of oxygen. Okay, so you are seeing peaks of all the elements that you are expecting in the sample. Other than that, you see peaks due to chlorine. This particular peak is because this palladium was taken as palladium chloride, and we see that some chlorine is still present. So by what I mean to say is that even if you are not given any information about the sample, by running a survey scan or a void scan, we can know about all the elements that are present on the sample. By taking the area under that curve, we can quantify and try to get information about the concentration of the elements that are present in the sample. So by simply, without any information, you can run the sample by using void scan or survey scan, you can get information about all the elements that are there on the sample. Okay. Now, our interest, as you all know, palladium is the active species on this catalyst, which means that it has to undergo some redox reactions. But this is a first initial fresh catalyst. So this was reduced with hydrogen, which means that palladium was mostly as metallic. So that is why you see a peak at around 335 electron volts, which is due to palladium 0. And this particular peak, which you see, is due to palladium 2+. That is because of the chlorine that maybe the bond one which is to chlorine. So the simultaneous presence of an element in multivalent states can be very clearly seen in this particular narrow scan of palladium. Well, carbon, they are all there, but our interest is to know the oxidation state of palladium because we have reduced it with hydrogen gas. So whether this reduction, that is the metal formation of the metal, is complete or not, if you do a XPS, you will see that most of it is palladium metal, but still there is some palladium 2+ still present, and this particular peak is around 337 electron volts. I will tell you with one more example. This is a clear example which gives us an idea about the beauty of the technique where you can see their multi-oxidation elements present on the sample. This is also our own work where we have taken polyvinyl alcohol films with the palladium as the metal, and we have tried to develop this. Initially, the film, the concentration is about 0.09%, and before heating, we could see this palladium 2+ around 337 electron volts. As we heated this film at about 130 degrees for 30 minutes, you can see the appearance of peaks that are due to palladium 0. Okay, as we heated for a little larger, that's about 120 minutes, the intensity of the peak increased still further. Okay, so in this one, we have taken a little higher concentration, temperature maintained same, but in only 60 minutes, we could see palladium 0 much more compared to palladium 2+. So here again, we are seeing the simultaneous presence of metal in its multi-oxidation state, and by taking the area under the curve, we can quantify and know their concentrations in their oxidation states as well. This is another work of our own, where it's a DST project where we try to work on the various Ayurvedic medicines, the bhasmas, and we try to work on it. And though these bhasmas have been used since ages, but the efficacy of these materials was not understood. So we tried to work on this where this bhasma called Makaradwaja, where gold is an active species here. But all of us know that gold is an inert material, and that is why we use them as the ornaments. But in this particular bhasma, it because of their processing, due to the processing steps that they take during the process, the synthesis of this material, it is seen that gold metal 0 gets converted into the ionic form of gold, and this peak is around 85.96 electron volts. And the efficacy of the medicine is not because of the inert gold, but it is due to this ionic form of gold at higher binding energy peaks. So, so like this, we have tried to work on various bhasmas like Tamra Bhasma, Rajata Bhasma, and so many things. And because it's a big project where we try to work on all these things at various processing steps and try to see how the intensity of the active species was changing, and their studies were done by in a different different angles, and try to get an idea about this. But what here the importance here is the efficacy of the medicine appears to be not because of the metal, but it is because of the ionic form of gold which is there. And these days, because of these properties, there are many studies in catalysis where people are able to get products from in greener conditions like water, room temperature, and trying to get many different products in green atmosphere, green conditions, than are going into harsh conditions that were known before. So that is how gold chemistry is catching up very fast. This is also our own work where we try to work on the various oxidation states of chromium. As you all know, chromium, molybdenum are such elements where they are present in multi-oxidation states starting from 2, 3, 4, 5, and 6 this thing. So we try to work on ferrous saponate as a substance through when the chromium containing solvent was passed through this ferrous saponate. After going through this catalyst, the hexavalent, the reduction of hexavalent chromium was possible, which means that toxic chromium could be made into a chromium which is a little better. So this is one another study where we try to work on this kind of things. And this is a magnetic material which we have used for our catalytic analysis. So here again, all of you know that this is the structure where you have both iron 2+ and iron 3+ in tetrahedral and octahedral coordination. Well, we cannot talk about the coordinations here, but what is important is that Fe3+ is both in tetrahedral and octahedral coordination. And in this octahedral coordination, it is Fe2+ and Fe 50% of them are jumping between Fe2+ and Fe3+, which means that the magnetite has both Fe iron present in both Fe2+ and Fe3+ states. So when you try to look at here, the characteristic peaks of iron are around 700 electron volts. So that is what you see here. And the high resolution narrow scans can be seen here. So in metallic form, it is around 707 electron volts. Fe2+ is around 79 to 711 electron volts. And Fe2+ is about 13 to 14 electron volts. So depending on the position, you can very clearly see the presence of both iron and iron 2+ and iron 3+ very clearly in this kind of magnetite. But as you all know, but there are various techniques that can be used for doing this. Most of the other techniques that are which can give an idea is like Mossberg or something, but that has its limitation. Here you get an idea. It doesn't mean that you can get an information about the metal, its oxidation states very clearly in this particular analysis sample. For example, you can use electron spin resonance also for knowing for analyzing this sample, but you will get information about Fe3+ alone, but not Fe2+. This is D5 configuration. So unfilled electrons you will get here, but in this case, the unpaired electrons are not there, so you will not see any electron spin resonance peak spectrum. So that means it has its limitation there. But in this technique, simultaneous presence of an element in its multivalent states can be very clearly seen in this technique. Now let us come to know about the satellite peaks. Oh, it's already 10:30, is it? Okay, I have to go a little faster. Okay, the satellite peaks are shake off and shake up, two different kinds. And the way they are performing is because of this. As you can see here, when they are leaving the sample, they are losing some energy here. That is the reason you get peaks due to shake up. And the other one is what is called shake off, where along with that energy, because of this energy, you're getting another energy, photoelectron coming out of it. And so this is which means that it's above its ionization energy, and that is the reason you see some peaks like this. So these are because of shake up and shake off peaks, and mostly these kind of satellite peaks are observed when in transition metal ions, and mostly in oxide form, and that too in higher concentration. So that in this case we are talking about magnesium here, manganese here. So mostly transition metal ions present in higher concentrations in oxide form, you will see these kind of satellite peaks due to shake up and shake off peaks. Now I'll go a little faster here. Maybe I've taken a little longer time in the earlier stages. Now let us try to look at these depth profiling techniques, which can be either non-destructive or destructive. So non-destructive, and I will try to explain this here. This angular dependence XPS is what is called a non-destructive technique, because you just try to rotate the sample along the axis, X-ray axis, and try to get information about the surface. So initially, if you have done like this, you're getting information from the depth, and you're getting a spectrum like this. But when the same sample is rotated along the axis, the X-rays are falling onto the surface, and you see that information that was otherwise hidden in this kind of this spectrum are very clearly seen here by only doing what is called a rotation. So that is the reason it is called an angular dependence XPS. And because you are not playing with the sample, it is a non-destructive technique. Now, the other one is the destructive depth profiling, where you have, you use argon ion sputtering for, removing the surface and trying to do the analysis. So what you do is you first do the XPS spectrum analysis here. Then you irradiate with argon ions and remove few layers. So which means that once you have sputtered the surface, it is removed for once forever. So that means you are playing with the sample. So this is that is the reason it is called a destructive depth profiling. So you sputter the sample, remove the first few layers, do the XPS again, and then again do the sputtering, do the XPS again. So this cycle continues. So because you are playing with the sample, it is a destructive depth profiling technique. So as I said, most of the times these are used for semiconducting applications. And if you have something some sample like this with the titanium nitride, silica, and silicon substrate, you do this kind of analysis. And you can see here, initially the oxide peak, which is around 104 electron volts. And then slowly it is the elemental peak, which is around 99 electron volts. So by doing so, you can know about the depth of the layers. If you have done deep into the sample, you can know the depth of the layers and try to know the sample at the interface also, and try to get information. So this is another example. Okay, the quantification is done by something like this. There's so many things that are there here, from the atoms per centimeter squared, photoelectron, that is the flux, that is the photoelectron cross section, the X-ray flux, the detection efficiency, all these things are there. But all these narrow down to the intensity of the photoelectron peak and the sensitivity factor of the relative sensitivity factor of the element. So as you can see here in this particular example, there are two different peaks of nickel and iron at their positions, and the full width half max is there. The raw area, that is the area under the curve, is given here. Relative sensitivity factors of the element, which is characteristic of the element. These parameters, we can know about the concentration of these elements, either in atomic mass concentration or mass concentration or concentration percentages, like this. This is our own example here. where we have tried to synthesize these materials in different compositions, and we try to correlate our data with our EDX. As you can see here, both the data that is obtained from EDX as well as XPS are pretty close, and sometimes a little better in XPS, because you are looking at the surface and trying to get better information when compared to the bulk here. Okay, this, as I told, we can also do the system in imaging mode. So by doing so, we are using this hemisphere circle on the above and trying to do the analysis. So by putting a spot onto the surface, once we take the imaging of the surface, we can take wide scans at that particular point and try to know where is, in this case, where is it is iron rich or where it is titanium rich, and try to understand. So even the narrow scans can be understood by here, and we try to get information about the areas of our interest. So this is what is called XPS imaging, where you quantify. You can quantify and take the areas and concentration of the materials. So this is iron oxide here. So iron, titanium oxide is here. So iron and oxygen. When you overlay this, you will get an image of what is called the iron oxide imaging, and so on. So you can see that wherever there is this iron is present, you see because oxygen is also there, but you don't see that kind of concentration, concentrated image on the sample. So this is a gold grid that we normally use for standard the calibration of the image. So by doing so, you can know about the thickness of the grid and the distance between these two simultaneous thin grids and so on, which is what is called field of view in case of the new system that is there, which is called field of view. And by changing this field of view, you can take from smaller areas to larger areas, because this is the max, that is 800 microns of field of view. This is 400, this is 200, and so on. So yeah, as I told you, we can measure and try to know the thickness of this particular grid and the distance between these two grids and so on. Okay. This is, well, that was about the technique. So where I have tried to explain about X-ray photoelectron spectroscopy, in which X-rays fall on the sample and photoelectrons are ejected. These ejected photoelectrons give us valuable information about the elements present, their oxidation state, and their molecular environment. And I've tried to explain about quantification, about the imaging technique, and so on. So those are and I've given an idea about the spin orbit splitting and how it is characteristic of the elements in P, D, and F orbitals, and how to measure what are the two peaks that you identify in spin orbit splitting, and how those values you are getting, and how is the area under the curve, and the ratios that you see in spin orbit splitting are characteristic of the elements. So that's a brief thing about the XPS part of it. And though I thought I'll talk in detail about my work, at least to give you an idea about what I have done during my stay at Indian Institute of Chemical Technology. These are some things I worked on: core shell nanoparticles, polyaniline nanostructures, gamma acacia stabilized metal nanoparticles, magnetic separable nanoparticles, biomimicking or biomineralization. These are some things that I have worked on, and I use these materials because most of the characterization was done by me itself, like by XPS or UV, whatever it is. So most of all the kind of characterizations done by me, by TM also. And these studies, the samples that were prepared, were used for various organic transformations. I think I'll not talk about all this in detail, but I'll just go through the slides for your interest. So these are the gamma acacia stabilized metal nanoparticles, which we have studied, and this is the reaction that we have tried to work on. So conventionally, you see that you have so many reducing agents, halogenic agent base, which is generated as a waste here. But in with these palladium nanoparticles, you can directly use them in methanol and in the hydrogen atmosphere to get your desired product. In core shell particles, you have something like this. These are the different core shell nanoparticles. So, well, normally these silica nanoparticles are having OH terminals on their surface, and but these metal nanoparticles, when you want to put them onto the surface as shell material, they do not allow. For that, you do what is called surface functionalization. In this case, we have used the 3-aminopropyl triethoxysilane, and then you have these NH2 terminals on this. Now you can add your metals and then try to reduce them and have them as the core shell nanoparticles, as you can see here in this chem image. These are the hollow particles that we have synthesized of iron oxide. You can see that. And these are the magnetic nanoparticles that we try to work on. So when you are using these materials for catalytic applications, it is easy to separate them from the reaction mixture by just placing a magnet next to it. So that is the reason we have tried to study a little bit on magnetic nanoparticles. People who are interested to know about these magnetic nanoparticles in detail, maybe you can look at this Anglo Chemie paper and try to understand in detail. Okay, okay. And later we try to work on water splitting reactions. And for that, we used photocatalytic reactions. And as you all know, these semiconducting materials are developed for light harvesting and of course for charge excitation. And most important thing is to have this charge separation and transfer. For that, you do all the tuning activities by incorporating various different materials so that these kind of recombination doesn't take place. And then you have this the electrocatalytic reactions happen at either the hydrogen site or the oxygen site here. That's a reduction in oxidation state. And these are some things that we have done. Okay, I will not talk much about here this. So these are some things that we have developed. And for further reading, I'm sorry, I'm having this cough problem. We are practical guides for X-ray photoelectron spectroscopy. You can look into all these these are the things. And NIST, and there are various websites where you can get all the information about the various binding energy peaks of the elements in their different molecular environments and try to understand them. So these are some of my students. My thanks to our director here, Srinivas Reddy. And these are the two instruments, that is the TEM and the XPS that I have used in the institute. And I consider them to be my two eyes in the institute because with these two techniques, I studied the beautiful world of nanoscience and nanotechnology. So that is the reason I consider them to be my two eyes in the institute. Well, all of you know her. When I happened to go to the Missionaries of Charity at Kolkata, these lines caught my attention. What I can do, you cannot. What you can do, I cannot. But together we can do something beautiful for God. So I think that nanotechnology is one such area. Well, as a matter of fact, research is such an area where all branches of sciences have to work together and come out with something beautiful for mankind. So I think these lines are very apt for our kind of work. So I normally end my talk here. So once again, I thank you all for your patient hearing. And whatever little I knew about this XPS, I have tried to explain. And if there are any questions, well, you can write to me at sridharboja@gmail.com, or you can even ask me now, and session is open for discussion. Once again, I thank Chennakeshwulu and Ramanujan Reddy for giving me this wonderful opportunity to interact with you online. Maybe sometime we will talk in detail about all this in person whenever there's an opportunity. Thank you very much for giving me this wonderful opportunity. Thank you.
Yes, Professor. Thank you. That was a very informative session and a deep, in-depth basics. Participants, you can post your comments or you can directly contact Prof's email address. Since there is a time constraint, we will have to go for next session. Okay, thank you, Professor. Thank you for
Thank you very much, sir. Thank you.
Hello, sir. Sir, you need to unmute, sir. Your mic is off.
Yes. Yeah.
Right, sir. Morning, sir.
Yeah, very good morning. So I think slide is visible.
Yes, sir. Visible, sir. Shall we
Okay.
start session now, sir?
Yes, actually time is already 10:50, so I will finish within that time limit, no issue.
It's okay. That's not
So
okay.
I'm audible to all of you?
Yes, sir.
Okay.
Let me start the session, sir.
Yeah.
Dear participants, now we are going for the next session, scanning electron microscopy and its application in the biological sciences by Dr. O.P. Chowdhury, Associate Professor, Department of Veterinary Autonomy, Bandiad, Punjab. Normally, he is a gold medalist in MSc Veterinary Science, and he is listed in the top 2% of world's most cited scientists elsewhere in Stanford University, Associated Editor, International Journal of Surgery, impact factor of 12.5, and Annals of Medicine, and Surgeon impact factor 1.5, and he has published various publications and citations. Now I welcome Professor Chowdhury to take over the session. Thank you, sir.
Thank you very much. So my topic is scanning electron microscope and its applications in biological sciences. As in previous lecture, I was hearing that sir told about the XPS and the TEM. So along with the TEM and XPS, you can also go through the scanning electron microscopy. So first of all, that what is electron microscope? So an electron microscope uses beam of electrons to illuminate a specimen and produce a magnified image as compared to the light microscopy. So light microscopy is generally used in most of the institutions, but by using scanning electron microscopy and transmission electron microscopy, you can enhance your studies and publish in very good journals. So an electron microscope has greater resolving power than a light powered optical microscope, which are generally using in the institutions, because the electron microscope uses the electrons, which are having the wavelengths about 1 lakh times shorter than the visible light. In the visible light, there is using of the photons. So when we are going to compare with the light with the electron microscope, so as we know that in light microscope, the source of the light is the visible light. And in the electron microscope, there is electrons, and approximately they are having 4 nanometers. And the maximum resolving power, this is very, very important. In case of the light microscope, it is 200 nanometers, but in case of the light electron microscope, it is 0.2 to 3 nanometer. And the maximum magnification. So in case of the light microscope, the maximum magnification, we can go up to the 1500x. And in case of the electron microscope, we can go up to the 1 lakh times. So it is very, it produces very magnified images as compared to the light microscope. So in radiation source, the light microscope uses the quartz halogen lamp. In case of the electron microscope, it uses the tungsten lamp. So in case of the lenses, there will be glass lens. In case of the light microscope, and in electron microscope, there will be magnets are used. So interior of the light microscope is air filled, and in case of the electron microscope, it is vacuum filled. And in case of the sectioning, when you are going to section the tissues, so we use hand microtome, and the slices are of 20,000 nanometer, and the whole cells are visible. But in case of the electron microscope, we use the ultra microtome, and the slices are of less than 50 nanometers. And we can visualize the different part of the cells. They are the endoplasmic reticulum, or the heterochromatin, euchromatin, Golgi bodies, nucleus. So these are the major differences in between the light and the electron microscope. So I am just discussing about the scanning electron microscope. So it is a device, and or it is a type of electron microscope that produces images of a sample by scanning it with a focused beam of electrons. So whatever the structures which are present over the sample, you can visualize by the scanning electron microscopy. But whenever you want to do the whenever you want to go through the sample internally at the cellular level, you have to go through the transmission electron microscope. So these are the different manufacturers of the electron microscope. That is the SAM along with the TAM. That is the Zeol. And Zeol and the Zeiss, they are the most common electron microscope which are used in the country here in India. So these are the FEI company also, Siemens also, and Tescan also. So these are the different manufacturers, and you have to import because all these companies or the manufacturers, they are located, they are not in our country, they are located outside to our country. So we have to import it from the foreign. So this is the complete assembly of the scanning electron microscope. Here you can see this is the computer here and attached with the SEM. So there is a specific software for this SEM. So for running this software also, there is a requirement of a particular technician who can handle it, because these are SAM and TAM are very sensitive instruments. So once they will be, they are not like other devices. Once they will improperly shut down 2 or 3 times, they may be dumb. So the requirement of proper handling of these instruments are very, very necessary. So you just going through the anatomy in a very, so you can see here, this is the anatomy of the SAM. So in the anatomy of the SAM, first is the electron gun from where the electron beams are passes through the anode. Then these beams will pass through the magnetic lenses, and there is scanning coil, very, very important. These scanning coils are important because they are important for they will pass the beams through the sample, and there is producing of some secondary electrons, and these secondary electrons will be detected by the scanning unit which is connected with the scanning electron microscope. So this is the anatomy of the scanning electron microscope. So these are the different components of the SAM. So there is an electron source, there is a tungsten. Tungsten is usually used in the scanning electron microscope electron source. Then there is the thermionic gun, then field emission gun, then electromagnetic or electrostatic lenses, vacuum chamber. Then there will be sample chamber and the stage. This is important for us because we have to keep our sample into the sample chamber to visualize the samples for the scanning electron microscopy. And I already told you that computer is attached with the scanning electron microscope to scan the produced images from the SAM. Then there are detectors. One or more detectors can be installed at the scanning electron microscope. And these are the secondary electron detectors, and then backscatter detectors, then diffracted backscatter detectors, and X-ray detectors. So these are the different detectors, and their function is different. So these electron source and amniotic gun and different sources, and these are not important because these are already installed into the electron microscope. The important thing is the sample chamber, the computer, and the detectors, because we have to know each and every function about these different detectors. Otherwise, we will not able to perform the scanning electron microscopy. So you can see here from the electron gun, these electrons will be produced and they will come in contact with the sample. And from the sample, there will be production of the secondary electrons, and they will be detected by the device which is connected with the scanning electron microscope, and the images will be produced into the computer. So this is a very complicated process, but I am simplifying what is the scanning electron microscopy and how you can perform in your studies to enhance or boost your publications. Mainly the important is to boost your publications. So here you can see that these are the steps which you can follow in the scanning electron microscopy sample processing. So first you have to collect the samples. The sample can be any biological sample. It may be hair, it may be different tissues of the body, it may be the different organs, skin also. So you can collect the samples and then you have to fix the samples. So fixation is done in case of the electron microscopy. The fixative generally used is the 2.5% glutaraldehyde. But in case of the normal histology, or whenever you are going to perform the histology, then there is we are using the formalin. So this fixative in case of the electron microscopy is costly as compared to the normal microscopy, that is a light microscopy. Then after fixation, we have to dehydrate the sample. So graded alcohol is used here. Then there is important thing. This is the critical point dryer. Whatever the moisture is remaining in case of the sample, it is removed by the critical point dryer. And here there is use of the liquid carbon dioxide. So this is also a separate instrument. I will tell you in next slides. So then after CPD, we have to mount the samples, process sample on the grid. And these grids are usually made up of the carbon. And then after that mounting of the sample, we have to do the gold or the platinum coating. So this section is very, very costly. So for processing of one sample for the scanning and the transmission electron microscopy, you have to pay around 2,000 to 3,000 rupees for one sample. And finally, we have to do the scanning electron microscopy. So first I told you that we have to collect the samples. So for collection of the sample, you can see here, these are the hairs which we have used for the scanning electron microscopy. Here you can see this is a piece of the liver and this is the intestine. You can collect whatever the sample you want to do. So simply after collection of these samples, then you have to cut these samples into 0.2 centimeter square, very, very small. So generally you can use the stereo microscope or you can simply cut it. So after cutting of these samples, then you have to fix these samples with the 2.5% glutaraldehyde, or you can use the Karnofsky fixative also. That is combination of the glutaraldehyde along with the paraformaldehyde. So these are commercially available. So you can order it. So and you can make the preparation and simply you can prepare your samples and you can send directly to the electron microscopy laboratory also for scanning electron microscopy. So after fixation of the samples, you have to dehydrate it, and there is you have to prepare the formulation of the graded alcohol. So simply you can keep into the 30%, then 50%, then 70%, then 80%, then 90%, and finally into the absolute alcohol. So this process is dehydration, and it is done with the alcohol. So after dehydration of the samples which you have fixed into the 2.5% glutaraldehyde, if there is some amount of the moisture is there, so we have to perform the critical point dryer. So this is a different instrument other than the scanning electron microscopy. So in this, the critical point dryer is the method of dehydrating biological tissues prior to examination in the scanning electron microscope. And you can see here, these are the liquid carbon dioxide cylinders which are attached with the CPD. So there is a specific pressure to dehydrate these samples with the liquid carbon dioxide, and these samples will be placed here, and it will be completely logged, and the process for the CPD takes around 40 to 50 minutes or 1 hour, depending on the size of the sample. So after critical point dryer, you can see here, these are the grids which are used for scanning electron microscopy, and just above the grid you can see here, these are the carbon coated. They are the carbon coated. These are the carbon tapes. So as you know, carbon grids usually provide a thin conductive layer that prevents sample charging. Very, very important. It prevents the sample charging and allowing for clear imaging of non-conductive materials, especially when performing EDS, that is for the elemental analysis, that is the energy dispersive X-ray spectroscopy EDS analysis. And it also minimizes image distortion caused by electrostatic buildup on the sample surface. So these are very, very important, that the grid which we are going to place in the chamber section of the scanning electron microscope, it should be properly coated with the carbon tape. These are the tapes, you have to place it, and you can place the different samples over it. And these samples should be completely dehydrated. Otherwise, when the electron beam will come over these samples, then your images, the produced images will be distorted. Then after mounting, there is one more step, that is a gold coating. So over the samples, we have to coat the gold or the platinum. So gold coating is done because gold is highly conductive and platinum is also highly conductive and chemical stable, which help to produce high quality images. So gold coating is used for scanning electron microscopy only. It is not using for the transmission electron microscopy. So gold prevents charging, promotes secondary electrons, and create a homogeneous surface that produces a detailed images for the scanning electron microscope. So you can see here, this is a device. You have to keep your grids here. You can see here there are 4 slots. So you can put your carbon grids here, and they will be gold coated after given period of time. Then you can adjust the sample. Finally, you have to adjust the sample that during the process of dehydration, during the process of CPD, during the process of gold coating, the alignment you can do after these steps. So what structure you are going to visualize. And if you will not do, it's not necessary, but trying to positioning your sample gives you better results as compared to the roughly just handling the samples and all. So after adjusting, then you have to examine your samples under the scanning electron microscope. So the samples can be tested for measurement at various magnifications. You can magnify your samples up to the 1 lakh times. Then you can do micrometry or the nanometry. You can do the biometry of your samples. And the systematic examination using various instruments resulted in detection of elements with their corresponding quantities. Whatever you are sampling, the sample you are keeping for the examination under SEM, by the EDS. EDS is a detector which is located in the SAM, or you can install new one EDS also. So this EDS is usually used for elemental analysis of different elements of the periodic table. So when you will use the EDS, the scanning electron microscope produce a graph, complete graph of the different elements which are present in the sample, which you have kept into the sample chamber of the scanning electron microscope. But the processing of the blood samples is a little bit different because blood is liquid, and the different samples you are taking, like hair or the liver or the kidney or the spleen, intestine, you can use directly on the carbon grid, but the blood is liquid, so you cannot place it on the carbon grids. So you have to make the smear. So simply you have to processing of the blood, just collect the blood from animal or the human beings. Then this you can see here, this is the blood. So after centrifugation, you will get 3 layers. So you can centrifuge on the standard time and standard RPM. So you will get the 3 layers. So one is the plasma layer, one is the buffy coat, and one is the red blood cell layer. So you have to remove this buffy coat layer to visualize the different cells of the blood. Okay, so it consists of, as you know, it consists of the platelets. There will be white blood cells, there will be red blood cells, and so these are the 3 important components of the blood cells. So simply you can centrifuge into the centrifuge machine. So it will separate the plasma, the buffy coat, and the red blood cells. So you, for scanning and the transmission electron microscopy, you have to remove this buffy coat layer. So to remove the buffy coat layer, simply you can see this is the buffy coat layer. So just by using the pipette, you can use the pipette and you can take this buffy coat and you can separate this buffy coat into the different test tube or Eppendorf tube, and the process which we have used for the different samples like liver, hair, kidney, spleen. So we have to mix the same amount of the 2.5% glutaraldehyde for the fixation of the buffy coat. So we have separated the buffy coat. So we have separated the Buffy coat, and in the Buffy coat, we have to mix same amount, equal amount of the 2.5% of glutaraldehyde to fix it. And after fixation, uh, we can send these fixed Buffy layer to the electron microscopy laboratory for preparing the smear and the evaluation of the blood cells. So this is the article which we have published over the standard protocol for preparation of the blood samples for electron microscopy. This is the standard protocol which is published in Annals of Medicine and Surgery. First time we have given the baseline for the preparation of the blood cells. You can visualize the different blood cells by this protocol. And the study you can perform on the blood cells. You can treat these blood cells with the different toxic elements, and you can give the animals with that some therapeutic doses, which can you can study the different blood cells, their action over them, what are the different elements which are causing the apoptosis, and how these blood cells are regenerating back. So this is a very good study you can perform at your institution, and I am assuring you that if you will do the SAM and TAM over the blood cells by comparing it with some toxic agents and their therapeutic values, it will be published in very good journal. So uses of SAM in biological sciences. So it provides ultrastructural studies, and you can do the elemental analysis of biological samples, and you can produce the magnification up to the 1 lakh times, as already told you, that as compared to the light microscopy, electron microscopy is better. So this is the SAM EDS. I told you that this is a device which is connected with the SAM for elemental analysis. So this is the elemental analysis of the hair, which we have done in the hair of goat. And here you can see that it has demonstrated different components, that is oxygen, carbon, then there will be aluminum, then potassium and sulfur. So these are the different compositions in case of the hair of the goat. So you can generate the data on the different species which are available at your respective places, and you can do the SAM elemental analysis. And these elemental analysis and the scanning electron microscopy of the hairs, these are very important in the forensic science also. Then you can see here, these are the different scanning electron microscopy EDS for the pecten oculi, that is present in the eye of the crystal in the owl, which we have recently published in the Microscopy Research and Technique, having impact factor of 2.7. So as I already told you, to improve and to enhance the quality of the article, you can perform the SAM, TAM and the EDS, which will give you the good impact factor articles also. So this you can see here, these are the different graphs which have been generated for the, like you can see here, this is the aluminum, sodium, then carbon, the oxygen, and these are the different elements in the crystal and the owl, the pecten oculi of these two birds. So you can see here, this is the scanning electron microscope of the Aedes mosquito. You can see how magnified, you can see the magnification of the images. So in over the wings, you can see these are the patterns which are present in the mosquito, and these are the magnified eyes, because mosquito having the compound eyes. So you can visualize the samples over the higher magnifications, and you can create biometry also for good studies. Here you can see this is the proventriculus, which is a part of the bird, and which we have produced different images. So you can see these are the epitheliums, and these are the cells which are visualized under the scanning electron microscopy. And I told you that whenever you are going to work on the blood, so blood is very good topic which you can opt for the scanning and the transmission electron microscopy. So these are some scanning electron micrographs of the red blood cells, and these are the leukocytes, lymphocytes, and monocytes, which are usually visualized under the scanning electron microscopy. And I told you that hair samples are usually used for the forensic analysis. So you can see here, this is the hair of the black buck. So you can see the different cuticle pattern over here, and this cuticle pattern, you will see different in the different domestic and the wild animals. So you can take the measurements here. You can see here, this is the 16 micrometer. You can take the complete diameter of the hair also, and you can, as we know, we will cut the hair, we will get one cortex here and one medulla here. So we can generate the medullary index of the hair of different domestic and the wild animal species, and we can create new database for the studies. So we can see here, this is the SAM micrograph of the testis, which we have used the testis of the dog. So we cut the samples, then processed and visualized under the scanning electron microscopy. So as we know, the Sertoli cell is a mother cell which nourishes the spermatozoa for the further development. So you can see here, this is the seminiferous tubule. Complete seminiferous tubule is visualized under the SAM, and seminiferous tubule consisting of the several bunches of the spermatozoa. So these are the different seminiferous tubule in the testis of the dog. And you can see here in the scanning electron microscope, this is complete spermatozoa, consists of the three part. One is the head, then midpiece, and the tail. That is attached to the sperm that is attached with the Sertoli cell in the scanning electron micrograph. So you can see here, you are getting very good images as compared to the light microscopy. Then this is the micrograph of the muscle of the poultry. You can see here, these are the muscle bundles, and each muscle bundle is consisting of the different fibers. So you can take the diameter of the fibers and you can conduct the studies over the muscle of the different species also. Then this is the epididymis of the pig. So we have conducted the recent study on the epididymis of the pig. So in the epididymis also, you will get the, because epididymis is a structure which is connecting the testis with the vas deferens. So you will get the mature spermatozoa here, because epididymis is usually act as a storage for the spermatozoa. So you can see here in the epididymis, you will get spermatozoa, and this study we have done on the pig. So these are the SAM micrographs of the pecten oculi of the crestal and the little owl. So in this, we have created the SAM micrographs, and you can see here, these are the different cells visualized over the pecten oculi and the little owl. So these scanning electron micrographs will enhance and boost your study, and you will get more insight as compared to the light microscopy. So this is my very short and brief topic, because already Sir took, so I don't want to go in detail, because you have to process your samples with the help of the institutions. You can go to AIIMS, you can go to the IIT, you can go to some CSIR institutions, which you have to produce your samples. You have to prepare your samples, and thus just give your samples along with the fee. They will process your samples for the imaging. And at the time of the imaging, you have to be there, because they will not able to properly visualize your samples without the reference images or your help. So thank you very much for giving me this opportunity to speak over the scanning electron microscopy. If anyone having doubt, you can take my email ID also, and I will help you in the interpretation of the results, interpretation of the images, and how you can send your samples to the AIIMS Delhi or the IIT Delhi. So they are processing samples. There is a nominal fee. I told you that for the SAM it is 3,000, for the TAM it is 4,000. But you will get very good results, and you can publish in very high quality journals. So thank you very much, Satyabhama Institute of Technology, for giving this opportunity to speak over very short topic, that is the scanning electron microscope and its applications in biological sciences. Thank you.
Yes, sir. That was an informative session, and thank you for your nice presentation.
Yes.
Participants, any other questions?
Yes, you can ask, because this is a very broad topic, but I have completed in very short lecture. But you have participants, anyone?
So they have a question, why we use glutaraldehyde for fixation?
Sir, glutaraldehyde, because for electron microscopy, we have to use this fixative only. Light in the normal light microscopy, we are using formalin. So this is the substitute for the electron microscopy. There is no specific reason behind it, but for the electron microscopy, for the SAM and the TAM, we have to use glutaraldehyde.
Participants, any other questions? You can unmute and ask to sir. Or you can post the comments in the chat box.
Hmm? Any comment? Yeah, just thank you
How
for.
to interpret the results?
Yes, actually, first of all, you will get some published article over the net. You can search like I am working on the thyroid gland. So there are several studies which have been done abroad also. So you can go through that images. So collect these images on the Google. Then you make your database, and with that database, you go to the where you are going to do the electron microscopy. You can go there and try to interpret. If there is problem, I told you that I can help you in detail. No problem. If you need some sources, if you need some links for the electron microscopy, I will provide you. I will provide you to the organizer, so you can share in the group which you have created to the participants.
Hi, sir. Okay, sir.
Mhm.
Participants, any other questions?
But this is very, very good era. Actually, you can perform the studies at your institution and publish in very good journals. Because publication nowadays it is a very, very challenging task.
Yes, sir. So if not, then I thank Dr. O.P. Chowdhury for a wonderful session. Though it's a short, it is a very basic, informative, and will be useful for all the researchers and scientists and professors. Thank you, sir.
Thank you very much. So I have completed in my time, so you can go all the session with the time. Okay. So thank
Yes.
you very much for giving me
Thank you
opportunity.
very much for your time and your understandability, sir. Thank you, sir.
Thank you. Thank you. Okay. Have a good day.
Dear participants, the next session will start by 11:30. So kindly be stay tuned the line. Be back in under 10 minutes. Thank you.
Hello, am I audible?
Yes, sir, you're audible, sir.
So are my slides visible?
Yes, sir.
Okay, and yeah, the transitions are fine.
Yes, sir. Shall we start the session, sir?
Yes, whenever.
Okay.
Yeah.
The participants, the next session is on solid state structural chemistry, solid state NMR and structural chemistry by Dr. Sheetal Kumar Jain, Indian Institute of Science and Indian Institute of Science, Bangalore. Sir is working as an assistant professor. His research is focused on developing new magnetic resonance spectroscopic methods and techniques to elucidate structural and dynamic details of renewable energy materials such as semiconductors for solar energy harvesting, catalyst for biomass energy conversion, reaction in electrolytes. Sir has published around 30 publications and he has a lot of experience in his research. So now I request Dr. Sheetal Kumar to take over the session. Thank you, sir.
Thank you for the kind introduction. So after, I was told that I should show some applications that can help in learning how to interpret solid state NMR. And based on that, what I decided is to show two examples, and depending on the time, we'll see one or two examples. Okay. So,
Okay, sure.
so the first example is from material that are used in alternative cement as alternative cements. Now I'll briefly introduce why we need such materials or why we need to design materials that are alternative to the cement. So the before I start, the team I would like to thank who contributed to this work. The samples were provided from Dr. Soradeep Gupta from Center of Sustainable Technologies at IISc and his student Pitabas who made those samples. Now there are DFT calculations that we did, and I will not show those results here, but those were done by Dr. Aslam Kuni Mohammed from IIT Madras. And the solid state NMR part was done by Nikita in my group and Dr. Amrit Venkatesh at National High Magnetic Field Lab, Florida, because we needed high field magnet. And here is my group with whom we discussed everything. So I would like to thank them. And again, thanks for listening and coming, showing up to the talk. So the introduction to the materials. So here, just a second, I need to move this slab somewhere. Okay. Okay, so the cement industry contributes humongously in CO2 emission, which is one of the problems, right? So the reason for that is that in the process of making the cement, we do this reaction where you can clearly see CO2 get emitted. And to stop this, there is a huge amount of research going on in finding binders. Basically, cement is one of the binders. So cement-less binders that do not emit CO2 to reduce their carbon footprint. Okay, so one of those examples is alkali activated binders. What are those? Those are aluminosilicate precursors, and the sources of aluminosilicates can be different, which some of these are listed here, which are fly ash or slag or silica fume or rice husk or industrial waste. Okay, and then we add them with alkali activators. These are metal hydroxides like sodium hydroxide, potassium hydroxide, or calcium hydroxide. And once we activate them, these materials start to show binding properties because, and we will look into their binding properties, why do they have those? And it has been shown by this researching group who are active in cement research that their binding properties are close to the cement binding, the standard cement binding. Now, in the pursuit of reducing the CO2 emission, there are two parts. One is we can control the emission, about which I already mentioned, that we can come up with a material that do not release CO2. But there is one step ahead, and one can see that if we can use the CO2 in our favor to further improve the properties of these materials. So CO2 emission is reduced by avoiding limestone as calcium salt. This is limestone, right? And then they show that by accelerated carbonation, that is, if you expose these materials to carbonation, their strengths further increase. So now to understand that how these properties increase or get affected by carbonation, we need to study or look closely into their structure, local structure and dynamics. So here is a sketch to give an idea that how the local structure and phases in a typical binding material look like. And it highlights that the system is far more complex to be studied that easily. And since there are many disordered phases, the standard XRD-based techniques have very limited access to the local information that we are looking for. So basically, there are aluminosilicate layers. So these chains kind of structures that we see here, right? These are like aluminosilicate, right? There are these alumina tetrahedra and silicon tetrahedra, and they are in the chain. Longer these chains, stronger the binding properties, the stronger the materials will be. Okay. Then there are interlayers. So there are these two chains, for example, and then there are interlayers. And in the interlayer, there can be some other alumina forms, right? Then there are these alkali metals and other metals, and then the water. So there are a complex chemical soup present here, and they all play a role in the change in the properties of these bulk properties of these materials. So how do we go for it? How do we look into the details of these structures? That's the question. Okay. So what we did is we used solid state NMR because that's what we do. So in solid state NMR, before we go into the details of how we will perform NMR, we wanted to introduce, I would like to introduce some nomenclatures here. So if a silicon atom is connected to 4 OH bonds, it's called Q0. Its chemical shift will be different. If one of them H is replaced by SiO-Si linkage, then it's called Q1. If two are replaced, it's called Q2, so on and so forth. So you can see in Q4, Si is surrounded by 4 SiO-Si bond linkages. Now, this is not the end of the story, because it's also possible that one or two of these SiO-X bonds is replaced by SiO-Al. So in principle, there are now, you can see enormous amount of possibilities are there. There can be SiO-Si, SiO-OH, SiO-Al, and any combination of these. The key point here is that if the number of protons replaced by aluminum or silicon, they are represented by this upper index here, 0, 1, 2, 3, and 4. 4 means all 4 protons are replaced, and they will have distinct chemical shifts. But in those distinct chemical shifts, if there is Q2, it can be Q2 like this, where Si is linked with one side Si, another side Al, or a Q2 like this, which is one side Si and other side also Si. Both will have very close chemical shifts. They will have different, but we need advanced techniques to distinct them with full confidence, actually. Now I want to introduce the systems that we studied, and we took two systems here. One was this GGBS plus fly ash. We called it GF, GGBS plus fly ash. And in another one, we added GGBS, fly ash, and a soil. So these samples were provided by our collaborators, as I mentioned earlier. And then both the samples, we exposed them to accelerated carbonation and without carbonation, so that the total number of samples became 4. GFSC, meaning that soil containing sample, carbonated. GFSNC, soil containing sample, non-carbonated. And similarly, GF, non-soil sample, there is no S, but carbonated. non-soil sample, non-carbonated. So these are the 4 samples that we will compare and study using Solstat NMR and other techniques also. Now, if you see that cement properties have been studied already and they are reported in this paper last year. And if you compare the samples here, you see that the 1-day strength. So these in cement, they measure the strength of the samples at 1 day and 28 day, and then they decide. So you can see that the 1-day strength increases in both the cases, whether it's GF or GFS sample, like with soil or without soil. In both the cases, the carbonation further increases its strength. So carbonation is helping. That's a good news. However, if you look at the 28th day, the carbonation effect is almost gone. It no longer matter. It may even further reduce the strength further, which is something that we need to be careful about. However, the 1-day strength is also important because as I mentioned here, for offsite construction, people make the small structures offsite, and it's important that within a day or quickly they can get rigid so that they get enough strength to be transported. So this is an important property which clearly increases with CO2 exposure. Why does that happen? That's what we will have to say. So then let's pinpoint the questions here. The questions are, how does soil addition affect the distribution of the local phases? Because now there are 2 types of sample, one with soil, one without soil. So are the local phases, like the structures in the beginning without carbonation, are the same or different already? Then how does carbonation impact the local structure? After that we carbonate them, and is this changing the local structure? We are almost certain they do, because their properties are changing. But then the question is, how are the structures changing? Are they increasing the chain length, or they affecting the porosity of the material? And how does the structural distribution influence the carbonation mechanism? This is a reverse question, because in the presence and absence of soil, the initial distribution could be different. If the initial structural distribution is different, will the carbonation have different mechanism in the 2 cases? That's another question. So to track down these questions, we use Solstat NMR, and those are the data that I'm going to show in this first project. Now, since it's workshop, so I just briefly introduce in 2 slides how do we use Solstat NMR. Basically, if you put a sample in a magnetic field, the nuclear spin energy levels get splitted into, like, due to the Zeeman splitting. And the energy gap between them is very small, in micro electron volt, that falls into radio frequency regime. That's why in NMR we use radio frequency pulses to perturb the system. Once we perturb the system, then we detect the signal, and that signal contains the information about the local structure. Why does it contain the information about the local structure? Because the Hamiltonian, if you look into it, it's a quantum system, because it's a spins, which is a quantum property. There is an effect of external magnetic field which leads to this splitting, but then there are chemical shifts, dipolar coupling, J coupling, quadrupolar coupling. These all are internal interactions that depend on the coordination number or internuclear distances or local symmetry and dynamics, and that fine-tunes this gap. So the frequency here is not only dependent strictly on the magnetic field or gamma, but other things also. And that fine change is detected in this signal, that frequency peaks, and that tells us the local structural information. Okay, so because it's a solid sample I'm talking about, in solution state NMR you don't need this step, but because it's solid and those interactions are anisotropic, that means if the crystal orientation changes, the frequency will change, frequency at which you see the NMR peak. And if all the crystal orientations are present in powder sample, then your spectrum will look something like this. It's a broad spectrum. You see 100 ppm broad spectrum you can get. So to reduce this broadening, we have to spin the sample at magic angle. Magic angle is called this angle here, 54.7 degree. This comes from the fact that the orientation dependence of the internal interactions have this factor into it. I will not go into the details here, but if somebody has a question, they can ask later. But if you put at this angle, the line narrowing is quite significant. But if you spin only 5 kilohertz, you get these kind of sidebands, depending on the anisotropy. So you have to spin really fast to get solution state NMR like spectra. Still, the spectrum can be broader than solution state NMR, but you can get a very narrow spectrum. So this is the simulation of the same sample which has large chemical shift anisotropy, and then with increasing the spinning frequency, we get peak narrowing. Okay. Now, coming back to our system, there are two challenges in using solid state NMR. First is sensitivity. I mentioned earlier that the splitting in the Zeeman splitting is very weak, microelectron volt. That means the population in the two levels are almost the same. That's why the solid state NMR sensitivity or NMR sensitivity is quite low. So you need a lot of sample, or you need to do some hyperpolarization tricks, which, if possible, I will cover in the second part of the talk. Furthermore, the natural abundance of these isotopes that are NMR active is not always 100%. They are often less. So that's also causes some change in the sensitivity, reduction in the sensitivity. So the materials that we are interested in, they contain these isotopes. We will be focusing in these isotopes, and their chemical shifts can be overlapping. For example, the silicon and aluminum are two important class of isotopes that we will use in this study. And if you look here, the chemical shift of Q4 falls into this range. So I already mentioned that Q0, Q1, Q2, Q3, Q4, they have different ranges of chemical shift. So we can distinguish them. But if you see closely, Q2 and Q4, but 3 of them are aluminum, they now overlap. So then we cannot distinguish whether it is a peak. If the peak falls at minus 90, for example, is it a Q2 or is it a Q3, Q4 with 3 aluminum? Those questions make NMR interpretation difficult. And therefore, we need really fast spinning, high magnetic fields, and correlation experiments, which I will introduce to interpret the spectra. Aluminum, the situation is significantly better than silicon, but still there are some cases where the chemical shifts overlap, and that make the data interpretation complex. Okay, so now with these, let's keep all those things in mind and start looking into the data. So there are two samples. So far, we did not carbonate any of those. So dashed lines are GGBS and fly ash. Solid line is GGBS, fly ash, and soil without carbonation in both the cases. And here are the spectra. This is aluminum spectrum. This is silicon spectrum. Both connected at 9.4 Tesla, that is 400 megahertz spectrometer. And the spinning was different in the two cases. Why the spinning was different? Because slow spinning allows you to take more sample. And in silicon case, we need more sample to get decent SNR, signal to noise ratio. Okay. The key difference here is these regions in aluminum NMR. Now, before we get into it, we should keep in mind that this region, this broad peak, I hope you can see my cursor, this region corresponds to AL4, that is sites with this kind of structures, right? And this region here near 0 ppm corresponds to AL6, octahedral phenomena. Okay. Now we see that without soil, there were some additional peaks here in the L4, but more or less the spectrum in AL4 region looks similar. However, in AL6 region, in the presence of soil, there are multiple peaks. In the absence of soil, mainly there is this one kind of peak present. So there is a larger distribution of AL6, the octahedral species of aluminum in soil case. Now let's look into the silicon NMR. Here we see the soil sample and non-soil sample, the dashed part. And we see that these regions, this is Q0 and Q1 region, which are more in non-soil sample. In the soil sample, most peaks are here. These intensities are higher, which are Q3, Q4. That is more silicon connected. Like these kind of specs. The examples are shown below in the structure. Right? There are less SiOH bonds present in the soil containing sample. So soil containing sample in a way is already more branched compared to the non-soil containing sample. That's information number one we got here. Now, to look into it with more detail, as I said, there can be multiple possibilities even in Q3, I showed earlier. How do we distinguish them? For that, we use cross polarization. And what is cross polarization? The pulse sequence looks something like this. Those who are not familiar with it, don't worry about it. The idea is we transfer the polarization, we excite the protons nearby. So suppose there are SiOH. Then we excite the protons and we transfer the polarization to Si. X can be Si or aluminum or any other. We transfer that. Now, this transfer of polarization will happen only if the proton or hydrogen is near X. That is, if there is SiOH bond. If it is not there, this polarization transfer will not happen. So this can help us in finding out whether there are Si linkages more or SiOH linkages are more. Right? Or same goes for the aluminum, where there are ALOH linkages present or not. Or are there water molecules very close to the aluminum? Because this is not true bond. This is true space polarization transfer, but the proton has to be in the proximity of the X nuclear spin, which can be silicon or aluminum. Now, here are some details how we do these experiments. Basically, the RF amplitude on both the channels should be satisfy this condition. So someone who wants to know more about it, they can ask me how to set these experiments. Okay. So now here are the results. Now, these black spectra I already showed. Now they are different. Earlier it was overlaid, which is the aluminum spectrum of soil containing sample and aluminum spectrum of non-soil containing sample. And remember that there were these extra peak here and there was this distribution here. Now in both the cases, when we do proton to aluminum CP, the spectra are shown in this magenta color in both the cases. And what we observe is that look into this non-soil containing sample first. The intensity of the tetragonal region significantly reduced and the relative intensity of octahedral region is higher. This clearly tells that Al6 octahedral aluminum, they have more ALOH. They are involved in these kind of studies, which are the structures are shown here. On the other hand, the Al4, majority of them, they do not have any ALOH structures. That means these which are shown here are not present and these kinds are more present in the sample. That's the indication. Of course, there are minor amounts present because the intensity is not zero with CP. Okay. And this happens in both the cases, with and without soil. Okay. But you see in both the cases, the Al6 region has significant peak intensity where this reduced significantly. Okay. So now we can do similar analysis on silicon and we did proton silicon CP. Now, if you see here, it's very interesting to note that these peaks in the near -70 to -80 ppm range, these peaks are supposed to be contain SiOH peaks because they have less number of SiOX linkages according to the chemical shift. If all are SiO, like for example, Si linkages, all four are present, those will fall into this region, -90. But surprisingly, while we expected a lot of CP here, we do not see any CP present in the magenta spectrum. These peaks reduced, especially in soil containing sample, the peak intensity almost goes from full to zero, while these two are still showing the CP spectrum. What does that mean? That basically means that these silicon the atoms, they have SiO linkages, but SiO minus. There is neither proton nor aluminum or silicon. Because if there are aluminum or silicon, they should have shifted this way. If there are proton, then this should have come this. So that means there are these negatively charged silicon tetrahedra. And that means their charge has to be balanced by these calcium 2 plus or sodium ions that are present. We will look into those later, but there are charge balancing cations present near these chains. That's what it means. Okay. Especially in soil containing samples, their intensity reduction is quite significant in this case. Okay. So now we got two information. Al6 have more protons, Al4 have less protons. Silicon case, there are charged silicon species that are present because there are SiO minus linkages present. Okay. Now we carbonate. Now we start looking into what happens to this distribution after carbonation. Now, the bottom spectra are aluminum and silicon with soil containing sample. When we carbonate, compare the black and the green spectra. Same sample before and after carbonation. The black spectra I already showed earlier. What happens in the green? The line gets enormously broadened. Even more, the Al6 region, this is aluminum octahedral region, there is a significant peak comes up. That means that introduction of carbon dioxide into this sample causes disorder, because in NMR, when there is more disorder, the lines become broad. So it causes disorder, and it converts some of the Al4 sites into Al6 sites. That's why these increased. Now, in without soil sample, this case, we see that broadening is still there. So disorder is increased. But in aluminum case, we do not see an increase in the Al6. So in the presence of soil, there is a conversion of Al4 to Al6. But that does not happen without soil upon carbonation. That's very important to keep in mind. Then if you see the silicon NMR here, what we observe is that this was the spectrum, the black one before carbonation. The green one is after carbonation. And what happens is that these charged species, we know by CP that these are the SiO4 minus kind of species. Their amount reduced, broadening increased, but these SiO Q4 type of studies, where all are SiO-Si or Q3 kind of species, they remained intact. So carbonation affects these charged species. That's number 2 that we can see from the comparison of before and after carbonation. Okay. In the case of non-soil containing sample, there is little information we can get because now everything is broadened out. So the features are almost. Nonetheless, in the soil containing sample, we clearly see a conversion of Al4 to Al6 and a reduction in the charge site upon carbonation of silicon. Now we can see more closely in the spinning side bands. Okay, that is the measure of their local symmetry and dynamics. And these are the folds for all 4 spectra. For the 4 samples, the 4 aluminum spectra are shown here. And you see that before carbonation, there are not that many spinning side bands. After carbonation, the strength of spinning side bands increases, especially if you compare the soil containing sample non-carbonated here to soil containing sample carbonated here. Now, what does that mean? That in the before carbonation, there were mobile sites. When there is mobility, there is less side bands. After carbonation, there are trapped in this kind of structure where the mobility reduced and hence the spinning side band increased. Okay. So carbonation reduced the SiO4 minus kind of sites, converted Al4 into Al6 type of sites, reduced the overall mobility of the aluminum sites. That means the branching increased after carbonation. That can explain why the one-day strength increased after carbonation, because chain length seemed to be increasing. Okay. Let's see we can do slightly more deeper analysis here now. So now here we are showing that what happens into the aluminum. Well, briefly I have discussed it, but now let's see. This is aluminum direct spectrum, and this is CP. The carbonate, this spectra we have seen before, that this is protonated, Al6 is protonated. That's why there is a more peak, right? Now, if you do the same analysis after carbonation, we now know the green spectrum, that after carbonation, the line width increased. But in CP, we don't see any spectrum left. That means after carbonation, there is no ALOH species observed. Now, here I would like to put a disclaimer that this one interpretation of this is that number of ALOH or Al sites, aluminum sites with proximal protons reduced after carbonation in both the cases. But because the lines are broadened, the cross polarization efficiency also goes down. So we need to keep that also in mind. Now, in the soil containing sample, it's very interesting to see that we observed earlier that this conversion happened Al4 to Al6. That's why there are more Al6 species now. And these Al6 species show CP. That means these Al6 species have protons on them. Okay. So that means what? That means initially, before carbonation, the distribution was something like that. There are Al6 species with protonated, and then there are Al4 species, but they should not have this many protons. This is not the right depiction. The number of protons should be less in Al4 species. But after detection, after carbonation, we see this a lot more Al6 formed based on this. Okay. Similarly, if you look into the silicon, which we already did, this spectrum number, the black and magenta comparison we already did. Now we are looking into the green comparison. Basic idea remains the same, that upon carbonation, the number of charge sites reduced, the number of core sites, which are all linked in SiO, SiO, or SiO-Al linkages, they do not change much, right? So that's what it means. Why does that happen? It can be guessed now at this point that because those charge sites, SiO4 sites, needed these cations nearby for charge balancing, like calcium 2+. If you introduce carbon dioxide, this calcium can be consumed by formation of CaCO3 or the carbonate. And when this forms, the SiO4- become unstable, forced to form more linkages, leading to higher amount of these SiO-Si linkages or SiO-Al linkages. That's a hypothesis. We can test that. To test that, we did ALO-Si correlation experiment. Now, correlation experiment is a 2D experiment in which we see, now earlier we saw in CP the linkages of the amount of protons that are nearby aluminum or silicon sites. Here we see the proximity of Al, aluminum, and silicon. Okay, so if they are close to each other, they should show a peak. If they are not, they should not show a peak. So in non-carbonated sample, we saw that the Q2 region of silicon and the Q3 region of silicon show linkages with aluminum. So there are ALOSI linkages present in soil containing sample. Now notice that these experiments were done at Florida magnetic field, high field magnetic lab, because we need high sensitivity. So we sent our samples there and these experiments were done there. Now we can observe this, but even there we could not observe the 2D spectrum of after carbonation sample because sensitivity was not sufficient. Nonetheless, before carbonation, there were ALOSI linkages present. That's what these results tell us. Okay, so then we looked into the aluminum more closely. To look into the aluminum sites more closely, we need to do some more advanced solid state NMR experiments, something known as multi-quantum NMR. What is multi-quantum NMR? we create double quantum coherence. I will not go into the technical details, but the spectrum look like a 2D NMR spectra like this. Now, in this spectrum, if all the peaks are on the diagonal, then they are highly mobile or well symmetric environment. If they deviate from the diagonal, that means their symmetry is distorted, either the crystal distortion or they became much more rigid, or both. That's what it is. So with that in mind, we started looking into the sodium NMR. Okay, because remember calcium and sodium, we did into both calcium and sodium because those are the ions, they play key role in charge balancing and stabilizing those negatively charged chains, SiO4 minus. So what happened to them before and after carbonation can give us some information. Okay, so that's why we did these experiments. Now, and we did these experiments in aluminum also, but that data I'm not showing here in the interest of time. So here, the sodium spectrum of the soil containing non-carbonated, so before carbonation and after carbonation. And we clearly see in the 2D that there are more number of peaks appearing after carbonation of sodium. Before carbonation, there are distribution, but after carbonation, there are clearly more number of peaks. In calcium NMR is really difficult to do. We do see some changes before and after carbonation, but we are still interpreting the data. Basically, we have interpreted it, but basic idea here is that various carbonate forms, phases are formed, right? Calcite forms and aragonite forms. These are being formed upon carbonation. Now, in sodium, because the sensitivity is higher, we see very interesting features here. And these features mean that sodium have this kind of hydration layer. The number of water can vary in the hydration shell of sodium. So the sodium that is close to the charged ion has less number of water into it. And as it goes away, the number of water can increase into it. And varying the number of water, we will see different types of peaks. That's what we see. So if you notice here, the projections or the 1D NMR also, that after carbonation, we see these nice features coming up, which were not there before carbonation. That means there are different sodium atoms present with varying degree of hydration around them. Okay, so in summary of this project, what we can see is by doing multi-nuclear NMR, that is aluminum, silicon, sodium, calcium, and also we did proton NMR, but that we are not showing here. We found out that first, in the presence of soil, there are more number of charged Si sites, SiO4 moieties present, and there is a distribution of Al4 and Al6. There are no Al5 present or minimal present. The carbonation increased the disorder in the system because the lines get broader, and the charged silicon sites got reduced after carbonation because they got destabilized due to the consumption of the charge balancing cation by CO2. And the metal ions got away from the chains and started forming carbonates with varying degree of hydrogen shells around them. So this ends the first part of the talk. And at this point, if you want, I can take some questions, and depending on time, I can go to the next part of the talks. So please let me know. Hello.
Yes, sir.
Yes. I'm just saying that first part of the talk is over. If you want, I can take some questions at this point.
Yes, participants, if you have any questions, you can unmute and ask the questions to sir.
Okay, if not, I don't know if there is some chain questions. Okay, if If not, I can now move forward and quickly cover a second part of the talk. Okay. Should we move? Okay. So I hope you can hear me still. So in this part of the talk, this is a slightly earlier work. We will investigate a double perovskite. So it's completely different material, but and we will not only use salt-state NMR, but we'll use EPR and DNP also. And the introduction to the system. But before going to that, this work was done in collaboration with when I was at UCSB, and this is the team at UCSB. Then Vlad at University of Alberta, who provided the sample. This is his team, and the group at UCSB, and these were the funding agencies. So the perovskite materials are important. They gained a lot of attention recently, especially after 2009 or so, because of their exotic or exciting photovoltaic properties. They can be used as highly efficient solar cells. However, there are some certain challenges, and those challenges include low stability. They have lead into him, so the lead toxicity is another problem. And when we try to replace the lead with some other alternatives, it turns out that the stability gets even lower, and the photovoltaic properties do not match as before. So the local structural information can help us in improving or retaining their photovoltaic properties while increasing their stability and reducing the toxicity. That's the idea. Those who don't know about the structure, the basic structure of these halide perovskites is given here. So these are ABX3 kind of material, where A is a cation, B is a bivalent cation with two positive charges, and X is the halide. And now people have made a combination of all with partially chlorine, iodine, bromine, and varying degree of the A sites and B sites. But basic structure is this. Now, the one alternative approach to improve the stability is double perovskites. Same structure, but basically now you can see that instead of one type of tetrahedra, octahedra, there are two, blue and red, corresponding to a structure which is A2, B1, B2, X6. Okay. So in this case, the second cation, which was B having 2+ charges, is replaced with one single and one triple charge, right? So it can be B1 can be sodium or silver, B2 can be any of those. And with that, the structure remains the same, charge gets balanced, and the stability is higher. However, the band gap increases. That means their photovoltaic properties are no longer useful. To overcome that challenge, the material scientists dope these materials with transition metals, for example, manganese, which will be our system of interest. So we have cesium, sodium, bismuth chloride, and we dope it with manganese, and we see what happens. So once we dope it with manganese, with 0.23% or 0. So there are two samples doped with 0.23% of manganese and 0.51% of manganese. Okay, so this is the pristine sample. These are the XRD data. Then doping and highly doped, slightly high doped sample. Their XRD do not show any major structural changes. However, the photovoltaic properties, on the other hand, are changed significantly. So then what's going on here? Are there some local distortions which could not be tracked using the XRD? And that's why we use salt-state NMR. Okay, so the key questions we posed for salt-state NMR is, first, let's confirm, is this manganese getting into the lattice or is it just clustered outside? If it is getting into the lattice, is it replacing bismuth or sodium or both? Is it getting distributed uniformly like showed in the picture 1, inside the lattice or getting clustered inside the lattice? These are the questions that we can address and find answers to, which can help in knowing why the doped material behaves the way it is. Okay. And as I mentioned earlier, here we will not just use the NMR, it is part of it, multinuclear solid state NMR, that is cesium, sodium, bismuth, chlorine NMR, we will use all of them. Then we will look into the manganese EPR and its EPR properties. And finally, if time permits, we'll see dynamic nuclear polarization, which is a new technique to study such materials. So the idea here is that because there is a paramagnetic species present in this system, manganese 2+, it affects the properties, NMR properties of neighboring nuclear spins. So their relaxation rates become faster, and that means their lines become broader. Not only that, these species are not spin half. So like in the previous example, we had sodium, aluminum. Here we have all those 4. That means they are quadrupolar. That means their quadrupolar interaction, which is highly symmetric. Briefly, we saw that the number of spinning side bands changes that is affected by the local symmetry and dynamics. So that's another key hint that we will look into. So basically, we will look into the chemical shifts, their spinning side bands, and the relaxation rates to find out to get the information about their local structure. So here are the NMR spectra of cesium and sodium of the 3 samples. Pristine sample, 0% doping, 0.23% and 0.51% of manganese. And the tables below show that the line widths, full width, half maximum line width, increases with manganese doping. Now, this is expected because manganese is paramagnetic. So if the paramagnetic species are present, the relaxation rates become faster, the lines become broad. Same happens in the case of sodium also. And there is a slight change in the chemical shifts. The chemical shift from 76.3, for example, in the case of cesium without doping, and it slowly gets all the way to 0.2 ppm shifts. Similarly, the similar shift is observed in sodium also. Now, these do not tell us much, but it definitely tells that manganese is getting in proximity to both cesium and sodium. Otherwise, their properties should not have been affected. Now you look into the bismuth NMR, right? This is interesting. The bismuth NMR shows a lot of side bands, that is large quadrupolar coupling. And if you look into the zoomed in version of these side bands here, this number of side bands is higher in the highly doped sample. In the pristine sample, there is almost no side band present in this range. That means the quadrupolar coupling is increasing with doping. That means the local symmetry around bismuth is getting changed upon manganese doping. But if you look into the line width, it's not changing. Or the chemical shift, it's not changing. Now, this indicates that the manganese is not getting close to bismuth, but the bismuth local symmetry is changed. Now, this we need to take with a pinch of salt because the change in line width is not observed, clearly not observed, but the line widths were large to begin with compared to the other 2. So could be that even though manganese is affecting it, but it's not significant enough to be observed. If we ignore that fact, then the interpretation would have been that manganese is replacing the bismuth. Because it is replacing the bismuth, the neighboring sites are sodium or cesium, which are getting affected, and the distortion caused by replacement of bismuth by manganese is causing the change in the quadrupolar interaction of bismuth, leading to these segments. However, we need to verify this very carefully because is it really the case? This is not the full evidence for it. Okay. Now we look into the chlorine NMR, and if you see chlorine NMR, the spectra are quite broad, which is expected. Chlorine NMR has large quadrupolar coupling. Look into their quadrupolar coupling. This is in megahertz, so 17 megahertz, which is huge quadrupolar coupling. And we do not observe any change in quadrupolar coupling as well as the chemical shifts. Now, here the key is that if the chlorines are near manganese, they are directly bonded to it, like they are MnCl6 minus complex. So those chlorines, because they are too close to manganese, we will not observe them. That means we are observing only the chlorines that are far from it. And that's why we do not observe any changes. So at this point, basically chlorine NMR is not giving us any useful information. Okay. Now let's turn to the EPR part. If we look into the manganese EPR after doping at low amount or higher amount, we see that the G values and the G values and the hyperfine coupling values. And based on the literature, several reports have been published that if the manganese is present in octahedral symmetry, then this will be the hyperfine coupling, 89.3 Gauss. That means it's clear that manganese is getting inside the lattice. We have answered that part based on NMR because NMR properties were affected. That means manganese was getting in proximity to sodium and cesium. And now based on the EPR, we know that this is in octahedral symmetry. That means manganese is getting inside the lattice. But we still don't know whether it is replacing bismuth or sodium. We have some hint that it may be replacing bismuth, but we don't know for sure. And is it getting distributed uniformly or non-uniformly clustered? So to look into that, we went to high field EPR, Q-band EPR, which is more difficult to do, and but doable nonetheless. And here are the two spectra and their fitting, simulation fitting. And here we observe better resolution. You see that G values are not exactly the same. There is slight change in the G values, but more importantly, something called D and E, which are zero field splitting parameters. These parameters are very sensitive to local symmetry. So manganese is in octahedral symmetry, but not fully symmetric system. There is a slight distortion, and that's why these values are non-zero. D and E values are non-zero. And you see that D and E both increases upon increasing the amount of doping, which tells that distortion increases upon increased doping. So that means introduction of the manganese causes higher distortion in the system. Now, to see its proximity with neighboring nuclear spins, like whether it's close to bismuth, sodium, or cesium, or chlorine, we did something called high score EPR. Now, I will not introduce or go into the details of this experiment, but this is 2D EPR spectrum, and this is a schematic. Here, there you see two regions are shown. On x-axis, on the positive side, like the first quadrant, positive x and positive y, the peaks weakly coupled will show, and in the negative, the peaks that are the nuclear spins that are strongly coupled will show up in this region. Okay, so we will get into, and this is the pulse sequence, but we will see how the spectrum look like and get an idea. So this was the EPR spectrum that I showed before, the 1D EPR spectrum of manganese, and we did at 3 different field values shown by these arrows, these high score NMR. And the high score NMR at 3 values are color coded. Green one, 1213 Gauss, the blue one, 1190 Gauss, and this red one, 1178 Gauss. Okay, these are shown, and we see peaks that are near diagonal in the positive quadrant, and the negative X value also, there are some peaks present. That means some of the nuclear spins are strongly coupled to the manganese, they are close to it, and some are weakly coupled. Now, here for reference, I have mentioned the Lama frequencies of the cesium, bismuth, sodium, and chlorine at the field where we did NMR. That is Q-band. Okay. So now, how do we interpret it? So let's take one of the EPR high score spectrum, which looks like this, and we try to fit it. So if we fit it with only cesium, then we only see this peak. If we fit it with sodium, then we see these 2 peaks, which are present, these 2 peaks. If we use chlorine 2 isotopes, we see that this region is, there are 2 types of chlorine that are getting affected, that are showing. So overall fitting looks something like this. And based on this fitting, we found out that manganese cesium couplings, manganese sodium couplings, and manganese chlorine coupling. The key point here is that we did not show any correlation corresponding to manganese bismuth. We tried it multiple times. That means that the manganese is not coupled with bismuth, which matches with the hypothesis based on NMR that the bismuth is getting replaced by manganese. And because it got replaced, the nearest neighbor to manganese are these sodium, cesium, and chlorine rather than the bismuth itself. Now, to see the uniformity, we did DNP. And here is a brief introduction to DNP. There is something called solid effect, which means that if one nuclear spin and one electron spins are coupled, then this is the energy level. And if we irradiate at one of those forbidden transitions, we get DNP enhancement. But the key here is that if we see the build-up curve and fit that, it can tell us whether it is mono-exponential or stressed exponential. So we will see that this is the EPR spectrum I showed before, but zoomed in version of 0.23% doped sample of manganese. Okay. Now with this, let's skip the instrumentation part. With this, if you do DNP, then what we get is this is the solid effect condition, right? We see this positive and negative enhancement at each peak, positive and negative enhancement. This is a typical solid effect. Solid effect means it implies that we did not at least observe the manganese clustering. I mean, this is not a confirmatory test, but if manganese clustering is present, the chances are that we will see a broad feature also that we did not observe. But more importantly, if we look into the build-up fitting, the contact time and fitting, we see that the highly doped sample is becoming mono-exponential. The completely undoped sample was also mono-exponential. So after this doping, 0.51%, the whole sample feels similar relaxation rate or build-up rate. That means the manganese is getting distributed uniformly inside the sample. So with that, I can conclude the second part that manganese is getting inside the lattice. There is some distortion, but not significant. And this is substituting bismuth and getting uniformly distributed throughout the region. With that, I finish my talk and thank you. You can ask if there are any questions.
Participants, any questions can ask to sir or post the questions in the chat box.
I can't see the chat box right now, but you can check.
Yes, sir, I'm checking, but there is no questions. Our participants, you can unmute your mic and you can ask the questions to sir.
Okay, if not, then that's pretty
Yes, sir,
much.
you can go ahead for the next topic.
Yeah. Thank you. Thank you for the invitation and thank you for listening.
Thank you, sir. That was a nice and a wonderful presentation. Now, participants, just wait for some time and then we stay tuned.
Okay. Shall I share the slides? Okay.
Make it slideshow, ma'am.
1 second. No?
And just check.
Slideshow எங்க இருக்கு slideshow போட சொல்றோம். Slideshow
தான் மேம்.
இதுவா?
Yes, ma'am.
ஓகே மேம்.
Can check the slides, ma'am. Shall we start, ma'am?
Yes, sir.
Dear participants, good afternoon to everyone present here. Now we have a session on sophisticated analytical instrument facility at IIT Madras by Dr. K.V. Rama. A short introduction about Dr. Rama. She is a technical officer from IIT Madras, Chennai, and she obtained her PhD in analytical chemistry from University of Madras. She has organized various workshops and presented some papers and delivered various lectures. Her research interest is on application of ICP OES to problems in analytical chemistry, environmental and electroanalytical chemistry. And she has a professional affiliation of life member of Indian Society of Analytical Scientists. Now I welcome ma'am. Now I welcome Dr. Rama to deliver over the session. Thank you, ma'am.
Thank you, organizers. I take this opportunity to thank Dr. Chennakay Solu and all the organizers who invited me to this forum. I'll be presenting a lecture on ICP OES. So the name ICP stands for inductively coupled plasma. It can also be called as ICP OES or AES. It is either optical emission spectrometer or atomic emission spectrometer. It is widely used for qualitative and quantitative analysis. Supposing we couple a mass spectrometer to that, we can extend the features to semi-quantitative, quantitative, isotope ratio, and isotope dilution methods. We can also couple HPLC or ion chromatograph to ICP-MS, where we can do inorganic speciation studies. If laser ablation is coupled to that, we can extend the studies to geological geography. The ICP-OES is widely an emission spectrometry. It is widely used for qualitative and quantitative estimation of metals and metalloids, ultra-trace, major, minor, and major levels of detection. It has got unmatched combination of sensitivity and speed of analysis. It is very widely used in inorganic, biological, geological, environmental, forensic, and archaeological applications. We'll go through this in this fashion. I'll quickly scan through the history of the technique, principle, theory, and instrumentation. There are two different spectrometers which are very widely used in the market. One is the sequential, the other one is a simultaneous mission. And we'll just go through the applications. Any ICP technique, we need a sample introduction system which comprises of a nebulizer, spray chamber, torch tube, a peristaltic pump. The grating used is either a Zerny-Turner grating or an eggshell grating. The detector is a photomultiplier tube for sequential analysis, and a group of photomultiplier tubes are a segmented charge-coupled device for a simultaneous mission. This technique was actually introduced in the year 1961 by Dr. Reed. He used this technique to grow crystals at high temperature. many updates were done on this. And it is actually Truitt and Robinson in the year 1970 who extended this technique to organic materials. A commercial sequential spectrometer was introduced in the market in 1972, and Greenfield et al. In the year 1975 introduced a commercial simultaneous spectrometer. These are the units which are very widely used in trace analysis. It is parts per million, parts per billion, parts per trillion, parts per quadrillion, and weight percentage. So normally this ICP technique is used for major, minor, trace, and ultra trace levels of quantification. In the ppm, it normally covers ppm and ppb. If we hook up a mass spectrometer, we can extend the technique to parts per trillion or parts per quadrillion levels. These are the elements which are not attempted by ICP, halogens, because it requires special optics for the transmission of very short wavelengths, and rare gases because ionization potential is very low. Carbon, hydrogen, nitrogen, and oxygen has very poor emission, and rubidium and cesium also very poor emission characteristics. The basic principle is of emission spectrometry is that atoms or ions at energized state tend to revert back to the lower energy state, and in so doing, they emit photons of energy. The emission intensity is directly proportional to the concentration. Plasma is actually defined as a cloud of electrons and ions held at high temperature. It is the fourth state of matter. This is a typical calibration graph used in emission studies. The y-axis is emission intensity, x is known concentrations. Normally, we plot a straight line graph. If we spike the unknown, it generates the emission intensity, which is interpolated to the x-axis through the graph. And this is a comparison between AAS and ICP. A is a single element method. We need a hollow cathode. Rubidium and cesium can be attempted, whereas boron, phosphorus, and sulfur are not attempted. Chemical interferences are predominant. It obeys Beer-Lambert's law. Linearity is limited. Analysis time is 1 minute per element. Sample required is 10 ml per element. Whereas in OEA, at ICP OEA, it's a multi-element technique. Argon plasma is a source of emission. Rubidium and cesium are not attempted. Boron, phosphorus, and sulfur possible. Spectral interferences are predominant. It obeys Saha's equation. Linearity is 5 to 6 orders higher, and you need just 30 seconds per element. 2 to 4 ml of sample per element is required. You can just see the plasma zone. This is actually called the preheating zone. This is the induction region. This is the initial radiation zone and normal analytical zone. The preheating zone is actually used for removing the solvent. The initial radiation zone and normal analytical zone are mainly used for excitation and ionization. We have two different kinds of plasma. One is called plasma in local thermal equilibrium, and the other one is a non-LTE plasma. Normally, in local thermal equilibrium, LTE plasmas, they are observed in the lower regions of the plasma as far as the initial radiation zone, which is characterized by a single temperature, higher enthalpy, low signal to noise, and less population of the higher excited by ionization states. Whereas in the non-LTE plasmas, they occur in the annular region around the sample column where the injector flow and the plasma downlet are in contact, and in the normal analytical zone. It exhibits lower enthalpy, higher signal to noise, and overpopulation of the excited by ionization states. A monoatomic gas is normally characterized by the following: electron temperature, which is kinetic energy of the electrons; gas temperature, kinetic energy of the atoms; excitation temperature, population of the various energy levels, which is Boltzmann equilibrium; ionization temperature, which is population of various ionization states, Saha equilibrium. Generally, in a gaseous cloud which contains more than one atom, there is a finite probability that emitted photons will be absorbed by atoms of the same kind. This phenomenon is called self-absorption. The distortion of the observed line profiles by inhomogeneous self-absorption is known as self-reversal. All these factors have to be taken into consideration when we are doing ICP analysis, especially in emission technique. And we just consider the ionization of M to M plus and plus electron. In LTE plasmas, plasma is a function of temperature. This is the Saha equation. You can see all the parameters are defined here. It depends on so many factors. Mass of the electron, Boltzmann constant, Planck's constant, ionization energy of the species, partition functions of the atom and ion. In non-LTE plasmas, they tend to exhibit overpopulation of the higher excited bar ionization states than the LTE plasmas. This will affect the value of the term 2 in the previous slide. This term, this partition function term, to shift to the equilibrium on the right side. So we have a metastable state also, which is involved in this emission techniques in the plasma. It is actually one which cannot deactivate by radiational decay because the transition is forbidden by the selection rules. Such states often have long lifetimes in comparison with the normal states. And argon generally has two metastable states, 11.49 electron volts and 11.66 electron volts. The excited state lifetime for the resonance lines are of the order of 10 power minus 8 seconds, whereas the metastable state has a lifetime of 10 power 6 times, which is greater than this value. The collision frequency between the atoms in the plasma is 10 power 9 per second. Hence, a metastable state with a lifetime of 10 power minus 3 seconds will undergo approximately 10 power 6 elastic collisions if it is not quenched before radiating. This is the reason why even if a element is present in trace or ultra trace levels, say 1 by 10 power 5, it has every likelihood that it will collide with an atom in the metastable state. And that is why this ICP-OS technique is able to detect that element, even at very low levels, say trace or ultra trace, provided the excitation energy of the metastable state is greater than the ionization energy of the colliding partner. We can just consider this ionization equilibria where M plus argon in the metastable state giving M plus argon plus electron. The brightness or radiance of that line is given by this expression. All the parameters are again defined here. I would like to bring your attention here. Just see that exponential and the partition functions are increasing with temperature, whereas the fraction of atoms remaining unionized decreases with temperature, and each spectral line has got a temperature at which its intensity is a maximum. And how to measure a temperature? The plasma is generally considered to be in thermodynamic equilibrium. It cannot be characterized using a single temperature. Hence, we need 4 different temperatures. Say excitation temperature, which is Boltzmann equilibrium, the ionization temperature, which is Saha equilibrium, the electron temperature, which is kinetic energy of the electrons, and the gas temperature, which is kinetic energy of the atoms. Just note that Tg is less than, T excitation is less than, T ion is less than T electron temperature. And this is the Boltzmann equilibrium. Supposing we have to introduce a sample into the plasma, there are 3 different routes. Any solid sample can either directly be introduced into the plasma through a DC arc, spark, or laser. If it is in the powder form, you can use a fluidized bed swirl cup. Or if it is in the molten form through an ultrasonic nebulizer, directly it can be taken to the plasma. If your starting sample is a liquid, it can be either directly using a peristaltic pump into the nebulizer, injected into the nebulizer, then there is a droplet setting chamber, desolvation chamber, and onto the plasma. Or it can be vaporized and then same route can be followed. If it is a gas, it can be directly taken into the plasma, provided it is converted into the corresponding hydrate. You can just see the processes that are taking place when the sample droplet is introduced. Initially, we have a solution, then it is desolvated into a solid, then it is vaporized, then it is atomized. You have the excitation metastable state of the atom, and then it is ionized. We have metastable state of the ion also. This is a pictorial representation of the same, the desolvation, vaporization, atomization, followed by ionization. We can just see how a plasma is generated. Argon gas is first swirled through the torch, then an RF power is applied to the load coil. A spark produces some free electrons in the atom. The free electrons are accelerated by the RF fields, causing further ionization and forming the plasma. The sample aerosol carrying the nebulizer flow punches a hole. Actually, the sample is introduced from the base of the plasma like this. This is the injector. So it will be injected through this tunnel. This is a typical plasma emission in the instrument. We can just see how the temperature profile varies. The center of the plasma is called the eye of the plasma. There we have a temperature around 10,000 Kelvin. It is progressively decreasing. In the tail flame, it is around 6,000 kelvins. It is identical to that of a Gaussian curve, decreasing progressively from a central point. Normally, tail flame is used for spectroscopic observation. And there are two different views available in the ICP-OES spectrometers. This is called a radial view or side-on ICP viewing. This is called an axial view or end-on ICP viewing. This radial design is very robust and it has got fewer interferences. It is very widely used in petrochemical and metallurgy. The axial design has got best sensitivity. It is very widely used in the environmental and chemical fields. You can just see the yttrium atom, ion, and the oxide emission in the, say, ICP discharge. Fasel constructed a torch which is called as a standard torch, and there are torches which are lesser in dimension than this and more in dimension than this. The lesser ones are called the mini torch, and the greater ones are called the maxi torch. So it is only the dimension. You can just see this. Normally, this torch tube is made up of 3 concentric quartz tubes. Through the outer tube, the coolant gas is flowing. Through the central tube, the plasma gas is flowing. Through the injector here, the sample aerosol is directly carried on to the eye of the plasma, and this is the tail flame. It is actually downward in shape. Normally, this tail flame is used for spectroscopic observation. This is a cross-flow nebulizer. This is a gem tip cross-flow nebulizer, a ruby and a sapphire tip. So, argon and the sample, they are meeting at right angles here, and the aerosol is formed here. This is a cross-flow nebulizer and a Scott spray chamber assembly. This is a gem tip nebulizer. This is a Scott spray chamber. It is made out of Rayton plastic. It is inert to all types of samples. This is a conventional main heart nebulizer. The sample is flowing through the center arm and the argon gas is flowing through the side arm. It is meeting at the tip and aerosol is formed here. Based on the nebulizer tip design, there are different classifications. The normal, what you see here is a type K nebulizer. And this is a maximum dissolved solids nebulizer. Here you can see it is also made up of Rayton plastic. The sample flows down the face of the nebulizer, disrupts the argon flow, and aerosol is formed here. This is a single pass spray chamber. The aerosol mist from the nebulizer will hit a flow spoiler. It's just a bulb. And the droplets of the order of 3 micrometer or less than that will move on to the torch tube. Almost 96% of the solution will go to the drain. This is a conventional ARL3410 ICP with mini torch. We had this instrument at SAFE from, say, for continuously for 10 years. It was installed in 91 and then they developed serious maintenance issues and it became obsolete in 2000. This is the torch cabin and this is a spectrometric part. So we'll just see how this sequential spectrometer works. The light emission from the plasma passes through lens, filter, then entrance slit, and there is a mirror here. The grating is normally a Zerny-Turner grating. It is moving from left to right. It is connected to a worm drive, which is driving this worm gear, and it is also connected to a stepper motor. So each step it is moving. To rotate this grating is called a step width. So it is actually passing for a specified integration time at the specified wavelength. And during that time, the light intensity will fall on the photomultiplier tube. This photomultiplier tube will convert the light photons into electrons. It will charge a capacitor. The capacitor will discharge at the end of the integration time. This discharge signal will be digitized by the instrumental electronics into number of counts, which is proportional to the strength of the light received by the photomultiplier tube. So that is how this sequential spectrometer works. It is scanning from left to right in the ascending order of wavelengths. So this is a detection limit program. Normally, there are 3 different factors which have to be considered when we are doing a quantitative analysis, and that too with an instrument of the kind of ICP-OES. We have detection limit, background equivalent concentration, and lowest quantity determinable concentration. Deduction limit is 2 times the standard deviation of the background emission. The precision at that concentration is 50%, and it is a semi-quantitative analysis. Background equivalent concentration is defined as that concentration which generates a signal which is equivalent to the background emission. Precision is 1%. It is 50 to 100 times greater than the deduction limit, and measurements are quantitative. Lowest quantity determinable concentration is defined as 10 times the standard deviation of the background emission. Precision is 10%. It is 5 times that of the deduction limit. Measurements are quantitative. So normally the deduction limit values will be less than BEC. BEC will be less than LQD. So the instrument manufacturers will give you all these details. To determine the concentrations between 0 and deduction limit, a standard addition method should be employed. So this is a typical line library entry. The manufacturers will give you all this information. If you take a particular element like manganese, there are 2 or more lines available. And all these parameters like atomic weight, detection limit, the range, everything they will give you. Supposing you want to work in the trace level, you normally select 257.61 because it covers the range 0.005 to 300 ppm. The other line normally we select when we are working at higher concentration, say minor or major levels. Supposing you take cadmium, it has got 3 different emissions, and the BEC is already given here. And you can see the interferences. The interferences are different, no, for each and every emission line. So normally if these elements are present in our sample when we are determining cadmium, we have to carry out inter-element correction. And normally in the wavelength information, it is specified in the ascending order of wavelengths. For example, if it is manganese, copper, and silver, we have selected 3 different emission lines. It is in the ascending order, and the LQD values are given here. This background correction points are selected from the plots of scan data, and of course, the line library interferences are specified here. Any ICP operation requires this sequence of methods. Like first, you will create a task with all the information, then the zero calibration, the wavelength refinement, calibrate with known standards, curve fitting, analyze samples, and we have optional options like normalization, internal standardization, scan for background and interference. In the zero calibration, we will aspirate deionized water. The grating will look for the argon wavelength. Then it will average out and locate the position of argon line. So whatever is argon generally has an emission around 330.3 nanometers. So whatever is below that is considered a UV range, and then it goes to the left, and whatever is higher than that is considered as a visible range and scans in the right. In the wavelength refinement process, we will take the highest standard we have prepared. It will be aspirated in the plasma, and it will locate the window. It will select the scan window for the particular line. And of course, calibrate with known standards. We will take 5 or more standards. Each standard will be aspirated in the plasma. Then a curve fit will be generated. And then we'll go to the analyze samples. We have optionals like normalization, internal standardization, scan for background and interference. We will see them one by one. So this is the wavelength refinement process. This is manganese 257.61. Manganese is generally emitted from the center of the plasma. So normally we choose this to refine the wavelength. You can just see the scan window is from 257.50972 to 257.7122. So this is 257.61. So it has located the manganese wavelength within this window from 257.5 to 257.7. And this is a curve fit. This curve fit is normally based on polynomial equations. We start with first order, second order, segmented, and higher degree polynomials are also used. That is called chemometric measurements. Chemometric measurements using ICP OES. So here we have selected a set of data. The lowest emission intensity is 1. The highest one is 31.523. And these are the theoretical concentrations. We have taken deionized water 2.5, 5.1, 7.7, 10.3, 12.9, and 20. So this is the first order curve fit. And this is a second order curve fit, and this is a segmented graph. For segmented graph, we have specified the point of segmentation to be 3, that is 5.174. So for the lower concentrations, it will select the first order graph. For the higher concentration, it defaults to a second order graph. You can see the other curve fit parameters like intercept, slope, curvature, root mean square error, everything. As we go from the first order to second order to segmented graph, the RMS error is minimized. So normally we choose a curve fit which has got least RMS error. It should be within 3% for any accurate analytical work. And this is of course a curve fit, first order, second order, and the third segmented graph. And how we get the results? Like supposing we select mercury, the wavelength is 194.227. The mean peak position using the wavelength refinement is 0029 nanometers. The mean peak intensity for this sample is 493,105 emission counts. And it has been analyzed for 3 or 4 times, and the RSD is given here, relative standard deviation. This is the net peak intensity. And supposing we are carrying out some interference corrections, there will be a change here. But we have not, for this analysis especially, we have not carried out any correction. So the mean net peak intensity remains the same. And the predicted concentration from the intensity is 100.129 ppm. And this is a pictorial representation of the interferences that are possible in this technique. Here you can see that the interfering line is underlying the analyte line. And this is called a wing overlap. This is the analyte and this is the interferent. And here you have the interferent as a continuum in the background. For this kind of interferences, a background correction is necessary. For this one, change in the resolution of the spectrometer can solve this kind of a problem. Whereas the first kind, you have to carry out the interelement correction. How an interelement correction is carried out? This is just a procedure, simple procedure. It shows the interference of copper on zinc. So we just prepare 10, 20, 50 ppm of copper. We are adding 10 ppm of zinc to all the 3 solutions. Calibrate for zinc using standards from 0 to 50. Then we will run all the above solutions to get the amounts of zinc X with varying percentage of copper. Then we will fit a curve to get the intercept and the slope. Column 3 and 4 will be generated based on the curve fit. We have to find the coefficient and it should be entered in the line which is selected in the wavelength information. And this is just to show how the acids can, addition of acids can affect the signal. You can just see, this is just aluminum and manganese emission. And nitric acid and phosphoric acid, if they are added to the sample, they can cause maximum deviation in this signal. Hence, background blank subtraction is very much needed for this technique. And internal standardization, this is also an optional method. It is generally used to compensate for the physical transport effects which are caused by the differences in the viscosity, surface tension, or TDS. And it is generally used to if the sample is transported from one place to another. It is how to carry out an internal standardization. There is some criterion for choosing the internal standard. It is added to all the standards and samples as a spike. It should not have a rich emission spectrum. It should be close to the analytes in the periodic table. It should be free from the interferences with or from the analytes. It should not be present other than as a spike. Precisely the same quantity should be added to the standard and the sample. Actual concentration is not important, but it should be below between 10 and 100 times the BEC. For example, in the determination of magnesium in the range 0.1 nanogram to 10 microgram, the internal standard used is molybdenum. 20 microgram of internal standard has been added. A calibration graph is generally a plot of emission intensity of the magnesium by molybdenum, because magnesium is our analyte, molybdenum is the internal standard, versus magnesium concentration. The commonly used internal standards are scandium, strontium, yttrium, indium, germanium, and molybdenum. Scandium can be used as an internal standard for yttrium. Yttrium can be used for scandium and vice versa. This procedure is called normalization or resloping. It avoids the tedium of running all the, supposing we have prepared 10 standards for a particular analysis, it avoids the tedium of running all the standards every time. Supposing we switch off the plasma and switch on, we just have to run the lowest and the highest. It will recalibrate the calibration graph according to the present working condition. It is very much useful when we are running more number of samples, say 100 or 200 samples per day. So once you switch off the plasma, this procedure can be adopted. So this is our current instrument. This is a simultaneous spectrometer, and it is PerkinElmer Optima 5000 dual view instrument. It is a simultaneous mission. Okay. This is the torch cabin, and this is the spectrometric part. We just go through this schematic. The emission from the plasma passes on through the computer controlled mirror. So we have two views here. This is the axial view, and this is the axial view, and this is the radial view. In the axial view, it directly falls on the computer controlled mirror. In the radial view, it passes through a spherical mirror, flat mirror, and then it enters the computer controlled mirror. From again here, there is a toroidal mirror, entrance slit, a collimator, then eggshell grating, schemic cast disperser, visible prism, compound lens, and visible detector. So whatever is passing through the cross disperser will reach the visible detector. Whatever is reflected from the surface of the cross disperser will pass through a camera, UV camera, then fold a flat mirror, field flattener, then onto the UV detector. So how this eggshell spectrometer works? It scans in the UV range, say 165 to 403 nanometers. In the visible range, it is 404 to 782 nanometers. It has got 4 different modules, say transfer optics, input module, UV module, and the visible module. The transfer optics comprises of a computer-controlled mirror for radial and axial view. There is an automatic shutter mechanism which minimizes UV exposure on the first mirror. There is a mercury pen lamp for wavelength calibration. In the input module, there is a computer-controlled slit mechanism for high resolution, normal resolution, and low resolution. The light from the plasma is collimated and sent to the eggshell grating, which has got a ruling density of 79 lines per millimeter. The eggshell grating produces multiple overlapping diffraction orders with very good efficiency in each of the orders. The resolution changes as a function of wavelength. So you can just see the incident diffracted rays in the eggshell grating and the eggshell grating. It's just like a saw. So this is the incident ray and the diffracted ray. In the eggshell grating, it is just like a step, no? So it is just, this is the incident ray and the reflected ray. And this is a comparison showing the resolution for a sampling of data points at different wavelengths. So it's the graph shows 190 to 590 nanometers with bandwidth FW full width at half maximum in the y-axis. The resolution changes as a function of wavelength. At lower wavelengths, a very good resolution is achieved. And coming to the UV module, the cross disperser separates the lights into visible and UV channels. Front surface is a coarse grating with a ruling density of 374 lines per millimeter. This separates or cross disperses the overlapping orders into 2D eggshell pattern. The surface has a small waveform which corrects for spherical aberrations. Hence, UV channel has excellent optical throughput. Camera sphere generates spherical aberrations, deflects the light onto the detector, provides good focus on the entire UV. Detector is a segmented charge coupled device detector. This is a schematic representation of an eggshell-ogram. In the visible module, the overlapping orders from the eggshell grating will pass through the opening in the center of the cross disperser to the visible prism. The prism separates them into discrete orders. A 2D pattern or eggshell-ogram is produced. A compound lens directs the beam onto the detector, which is SCD. This is the segmented array charge coupled device detector. It is a silicon chip with a surface area 13 mm by 19 mm. And the surface has linear subarrays comprised of pixels. The subarrays are positioned on the detector at XY locations that correspond to the locations of the desired emission lines generated by the spectrometer, eggshell spectrometer. And the emission lines are detected by means of their location on the chip. The eggshell pattern is represented with emission lines on the y-axis versus diffraction orders on the x-axis. So this is the representation of eggshell pattern on the detector. You can just see that there are few lines given here, 167.017 nanometers, copper 221.458, and then titanium 368.520. The height and the width of this pixel will vary according to the eggshell pattern that is generated by the grating. And each linear subarray will contain 8 to 40 pixels. Each pixel is some 25 micrometer wide and 100 micrometer in height. And the emission line for the analyte of interest falls on the subarray along with the spectral information on each side of the peak. The analyte peak and the spectral background are measured simultaneously. This is the detector subarray pattern. It has got a photosensitive register, storage register, output electronics, interface logic, surrounded by a guard band. So normally in this 5300 model, it consists of 235 such subarrays depending on the wavelength. The subarray consists of 3 areas, say photosensitive register, which converts the photons into photoelectrons. The photoelectrons are stored as electrical charges in the storage register. And then during the integration time, the charge in the storage register moves on to the output register. There is a change in the electrical potential. The charge in the output register moves on to the output electronics, amplified, and then sent for signal processing. So you can just see we have aspirated a blank and then 10 ppm standard, 50 ppm standard, and 100 ppm standard. So this is the 100 ppm standard. All the other standards, the emission intensity falls within that window. The scan window is 327.9 to 328.09. This is silver emission. And once the calibration is done, we get, since it's a simultaneous spectrometer, get everything in one shot. It's just like a photograph. So this is how the results will be displayed. We give the commands here, and then corresponding emission spectrum will be displayed. And then as we aspirate the standards one by one, the calibration graph will also be displayed. So everything we can view in the same window. So how the results are presented? For example, we have taken one copper standard and then we have run the same standard 3 times. And from the emission intensity, the predicted concentration is 2.54. So it is a standard deviation, relative standard deviation, mean peak, mean corrected intensity, everything is displayed. How do you prepare the standards? We have an array of procedure like in the sample preparation, initial phase is sample collection, then dissolution and storage. Then we will be, first step is digestion with mineral acids, or we can do a dry ashing in a muffle furnace, or open and microwave digestion procedure can be followed. If it is a sample which is a refractory oxide, fusion and fusion mixer can be used to fuse the sample with the sodium and potassium carbonate mixer. That will be converted into the sodium or potassium salt, which will be easy, which we can dissolve easily in DI water. Solvent extraction methods can be adopted. Ion exchange methods can be adopted to pre-concentrate the element. When some elements, for example, if you are taking environmental samples like sand, even with mechanical shaking using dilute mineral acids, we can extract the elements. Separation techniques can be adopted, and samples are preferably stored in plastic containers to avoid spillage and absorption of ions. How error is introduced in ICP analysis? Weighing bottle is a must. Actually, we have to use a weighing bottle with lid when we are weighing the samples. And we can use a digestion system, for example, a rotor-based system or the latest one. You can take just 10 to 50 milligrams of sample, 10 ml of dilute acid is added, either HCl, nitric acid or aqua regia, or any acid which is recommended by the journal article for that particular sample. And we can keep a microwave power of 400, 800 or 1200 watts depending on the type of sample. The RAM time will be 15 to 30 minutes. The hold time will be 15 minutes. The temperature is 120 to 250 degrees centigrade. We can vary this depending on the type of sample. So normally in the microwave digestion system, this procedure, digestion, heating, cooling, everything will be completed within half an hour. But the disadvantage of this rotor systems is you can use only one particular type of sample for digestion. But this difficulty has been overcome in the recent ones. They call it as a single reaction chamber or pressurized digestion cavity, where variety of samples can be digested at one stretch within the same time, and independent temperature and pressure sensors will be there. And we can also vary the acid chemistry for each sample. And the solution should be colorless. It can be colored or colorless, but it should be very clear. When you are subjecting it to ICP analysis, ultimately the solution should be very clear. And the glassware, whatever we are using, should be calibrated, pre-calibrated using standard procedures. And the makeup of the sample should be exact. Like it should be to a known volume. If it is a colored solution, or it should be, if it is the upper meniscus should be followed for if it is a colorless solution. An identical blank should be prepared, and it should be subjected to analysis before aspirating the samples. Dilution of the samples should be done as and when required, and calculation of weight percentage of solid samples. And this is just a simple calculation. Supposing we take copper sulfate pentahydrate, we take a known weight of the compound, and then just supplement it with, just multiply that by the number of atoms of copper. For example, in copper sulfate, there is 1 atom, then atomic weight of copper into 10 power 6 by molecular weight of the compound into volume in ml. This formula will give you the parts per million of the your base solution. And then there is another formula for calculating the weight percentage. It is just expressed in grams per 100 grams. This is the instrumental value in ppm. The volume we are diluting in ml, and then the further dilutions are carried out. The dilution factor should be incorporated into 10 power minus 4 by weight of our sample taken. So similarly, we can use this formula for any known sample. The first formula is used for known sample. The second formula is used to calculate the weight percentage from the instrumental value. This value is generated from ICP. So calculating the number of atoms, supposing we have an alloy which has 3 components A, B, and C. The weight percentage we have seen in the previous slide. The number of atoms of A equal to weight percentage of A by atomic weight of A. Similarly, we have to calculate for the other two, B and C. And the number of atoms of N1 is N1 by N1 plus N2 plus N3. Similarly, for N2 and N3. This formula is very much used to find out the stoichiometric ratio of the compound. For example, if somebody is preparing a crystal for XRD analysis, initially they will come to ICP lab for compositional analysis. They use this formula to get the number of atoms. Later on, they will verify this value with an accurate measurement in the XRD, single crystal XRD. So what are the applications? This technique is very widely employed for ultra trace, trace, minor and major multi-element analysis. It has got unmatched combination of sensitivity and speed of analysis. Very widely used in silicate rock analysis, geochemistry, water analysis, environmental samples, archaeological materials, analysis of metals, biological samples, and inorganic chemistry. This is a typical REA scheme. You can just see that the powdered rock sample is subjected to acid attack, and then it is dissolved in HCl, filtered, and then the residue is again ignited and fused with sodium hydroxide or possibly KHF2 or LiBO2. And then the filtrate and the residue are further combined. They are passed on to your Dovex ion exchange column. And we are using two elements here, 4 molar HCl fraction and then 1.7 molar HCl fraction. This 1.7 molar HCl fraction is discarded because it contains the bulk of major and trace elements. But whereas the 4 molar HCl fraction contains the REs, so it is further evaporated to dryness and then redissolved in 10% nitric acid and subjected to ICP OES for analysis of rare earth elements. The highlights of the RE analysis include the light REs like cerium, lanthanum, neodymium, they are relatively abundant. Middle and heavy REs like europium, dysprosium, ytterbium, lutetium, less than or equal to 1 or 0.1 microgram per gram in the sample. The elements show a decrease in the ionic radii from lanthanum to lutetium. There is a progressive change in the rate of uptake for the elements into some minerals. Garnet bar zircon tend to concentrate heavy rare earth elements than light REs. Europium can exist in 2 and 3 state and can also substitute calcium. Calcium feldspar or plagioclase will preferentially concentrate europium. The analysis of RE can provide diagnostic information on the origin bar formation of the rocks, minerals, and data on changes in the oxidation bar reduction conditions of the rocks. So the RE analysis will give you all this information, and the ultimate one is it can provide a diagnostic information on the origin and formation of rocks. Heavy metals. The toxic heavy metals occur in very small quantities in the Earth's crust. For example, less than 1000 ppm. Hence, it is termed as a trace metal. If the density is less than 5 into 10 power 3 kg per meter cube, it is called a light metal. If it is greater than this value, it is called as a heavy metal. The sources of heavy metal generally come from domestic wastewaters, urban runoff, agricultural activities, industrial wastewaters, mining activities, and jewelry. So everybody would have come across this plant. This is a water hyacinth in natural habitat. It is called by various names, like in Tamil they call it as Agaya Tamarai, and in Hindi they call it as Jal Kumbi, and in botanical name is actually Eichhornia crassus. So you can just see that this plant multiplies rapidly through offsets. It multiplies sideways. The root portion acts as a sink for heavy metals. The inflorescence is some 15 to 16 centimeter high, and then the leaves are swollen and spongy, and then it has got excellent capacity to assimilate heavy metals. So hence a survey was conducted way back in 96-97 to study the pollution status at 20 places in the Chennai city. And all the regions are designated here. So majority of them are Kuvam River and Adar River basins. Some of them are also tanks, ponds, like that. And some of them are naturally forming lakes also. And for seasonal study, we have just taken only 4 sites. And we have studied the same sites during 4 different seasons. Say it was also designated as first, second, third, and fourth quarterly. It is basically early monsoon, spring, and summer. So this is a geographical representation of the sites. It is actually these sites were selected so as to study the pollution status throughout the city, North Chennai, Central Chennai, and South Chennai. So we can just see this is a two-way ANOVA table generated for the survey studies. Two-way ANOVA calculations are very standard. And you can see that we have studied arsenic, cadmium, chromium, manganese, mercury, and zinc. So an analysis of variance is carried out between locations and between parts of the plant. And you can see this column is the value generated from the ICP-OES method. This proves that the method is 5 to 6 orders. It has got linearity 5 to 6 orders of magnitude than the conventional atomic absorption. You can see the range of values here. And similarly, in the seasonal study, we have studied between the seasons and between parts of the plant. And this column is the ICP-OES value in ppm. So based on whether the table calculated F is lesser than or greater than the table value, a pollution study was carried out. So we just observed that the pollution levels of arsenic, chromium, and manganese are uniform in the Kuvam and Adar River basins in all the 4 seasons study. And the extent of pollution of arsenic and manganese is similar whether it is a lake or canal. And the distribution of arsenic, chromium, and manganese in the leaf, stem, and root portions are similar. Its accumulation pattern did not evince any variation during the study period. In North Chennai, manganese and mercury are the major pollutants. In Central Chennai, arsenic, cadmium, manganese, mercury, and zinc showed similar distribution pattern. Among the sites studied, they are all Kuvam River locations. In South Chennai, the distribution of arsenic, cadmium, and manganese were similar among the places studied. Water hyacinth can be used as a bioindicator to predict the level of pollution. To control measures can be adopted. Water hyacinth lagoons can be constructed in the industrial effluent area to manage pollutants that are emanating from the effluents before letting it into the environment. A multi-element absorption study was carried out by dipping the plant in the multi-element solution comprising manganese, chromium, zinc, mercury, and cadmium. So in the trend we observed was the absorption of manganese was greater than chromium, than zinc, than mercury, and then cadmium. The same pattern was observed in the survey and seasonal studies. And this is again the concentration of arsenic in the sludge samples from 20 locations in the Chennai city. So during the study period, the location 4 and 15. 15 is Koturpuram and 4 is Thiruvattiur. It is a tank. And Koturpuram, Adayar River, they indicated very high values for arsenic. And this is again the concentration of arsenic in leaf, stem, and root portions in the water hyacinth plant from 20 locations at Chennai city, which is expressed in ppm. You can see the leaf, stem, and almost it is distributed equally. In some places, the stem and root evinced very high values. If in the case of arsenic, all the 3 parts evinced equal assimilation capacity for this particular toxic heavy metals. So we just concluded that arsenic tends to accumulate in leaf, stem, and root portions, whereas chromium tends to accumulate only in the leaf and stem. And cadmium, manganese, mercury, and zinc tend to accumulate more in the root tissues. They are all transition elements. And laboratory model experiments can also be performed to study the metal uptake, wastewater treatment, and the pollution control methods can be suggested based on the laboratory model experiments. Both dry, wet, and plant can be used as an ion exchanger. So batch and column methods can be adopted to predict the pattern of uptake. The absorption of metal ions or the chemical species is actually a metabolic process because there is a concentration gradient which is existing between the medium and the plant cells. There is no reliable method as such to study the kinetics of the mechanism of absorption. So how these metal ions cross the biological membrane barriers and enter into the plant tissues or particular cell of the plant where they begin to accumulate, it is still a mystery. Organic analysis by ICP, it can also be extended to organic analysis where wear metals in lubricating oils, solvent extracted geological materials, lead in gasoline, determination of copper, iron, nickel, phosphorus, silicon, and vanadium in cooking oils, analysis of organophosphates for trace contaminants, trace elements in antifreeze, all those analysis can be done using this technique. Higher boiling liquids like xylene, MIBK, and heptane 2,1 are normally used as the solvents for organic analysis. So this is just a reference. So this inductively coupled plasma by Thomson and Walsh, it's a Bible for this technique. It gives an extensive account of the improvisations carried out in the technology, instrumentation, as well as application. And we have a lot of review articles are also available. So I would suggest the audience here to go through this book, Thomson and Walsh. It's an excellent book on ICP-OES. It's a sort of Bible. And the representative journals where these articles are getting published, Analytica Chimica Acta, and then lot of journals, Analytical Chemistry Journal, Analyst, Applied Spectroscopy, Atomic Spectroscopy, Clinical Chemistry, Journal of Analytical Atomic Spectrometry, Journal of the Association of Official Analytical Chemists, Spectrochemica Acta, Talenta, they publish, lot of ICP, OES and MS articles are being published. And finally, we are just SAFE is in the process of installing a triple quad ICP-MS with ion chromatograph and laser ablation. the difference between this OES and ICP-MS is the triple quad machine can attain PPT and PPQ levels of detection. Normally, argon is used in the plasma and the nebulizer. Helium used in the kinetic energy discrimination process. Hydrogen and oxygen for the reaction chemistry. So we can carry out semi-quantitative, quantitative, isotope ratio, isotope dilution, aqueous analysis, organic analysis, samples dissolved in HF, and there is a nano particle separation module where nanoparticle separation and counting can be studied extensively. And argon gas dilution can be used for samples containing very high TDS, say 20% or high. And this ion chromatograph, when it is coupled with ICP-MS, can be very widely used for inorganic speciation of iron, mercury, chromium, and arsenic. For example, separation of chromium 3 and chromium 6, and then inorganic mercury and organic mercury, and all that. The laser ablation can also be coupled with ICP-MS to probe in-depth details in geological studies, and any insoluble material can be ablated with a laser, and the ablated material can be carried on to the ICP-MS inlet through a helium carrier. A standalone ion chromatograph can also be extensively used for quantification of cations, anions, amino acids, etc. in the parts per billion levels. And we are in the process of procuring a microwave digestion using a single reaction chamber or PDC technology. And the procurement is in process. A microwave power of 1500 watts with a heating temperature up to 300 degrees and a pressure range up to 190 bar is available. This has got excellent capacity to process samples of different types and digestion chemistries within the same run. So it saves a lot of time for the analyst. So this is the laser ablation we are, this is yet to be installed. So this is just give a glimpse of the interface region. So the sample from the plasma touch will enter the sampler cone and the skimmer cone. So this portion is in, it is in the room temperature, and here we have a high vacuum region. So it is around 3 to 4 tar here. Okay. The sample ion beam from the sample from this region will enter the sampler cone and then the skimmer cone. Then it enters ion optics. With very high vacuum is maintained here. There are turbomolecular pumps to maintain this, and then a roughing pump for the interface. So this is our ion chromatograph. So this is the pump region where the elements will be housed here, and we have a gradient pump and the isocratic pump. We can from through the software we can use choose the gradient or isocratic pump. In the gradient method of study, the element composition can be varied during analysis. And this is the region where the analytical and the guard columns are housed. And this cabin, we can house the detectors. And there is one more cabin, we can house the detectors. So ultimately, in this system, 6 different temperatures can be maintained. It is very widely used for separation processes, reverse phase analysis, and all that. Wherever speciation studies are involved, when it is coupled with the mass spectrometer. This is the range of values which these are the group of elements. You can just see that elements which are not possible by MS is hydrogen, oxygen, helium, neon, and argon. Rest and some unstable elements like berkelium, californium, etc. Otherwise, it is almost covering 97% of the periodic table. Okay, this is the sample introduction part in the ICP-MS. And we have just now, this is just a main heart nebulizer. So we have inlets for routine aqueous phase analysis, organic phase analysis, and then the argon gas dilution. We can admit gases through this ports. So this is how the sample is entering the torch tube. So this is just a slide to show the separation of chromium 3 and chromium 6. So this has been carried out with ICS 5000, Thermodynamics ICS 5000 machine. And column used is AS7. The mobile phase is 0.4 molar nitric acid. A very low limit of detection, say 0.2 and 0.38 nanogram per liter, has been achieved for the separation of chromium 3 and chromium 6. This is chromium 3 and this is chromium 6. And this is the typical ICP-MS diagram. Can you see that the sample from the nebulizer will enter the torch tube. So this is where the atomization and ionization part is carried out. And then this is the sampler cone, the skimmer cone, this is ion optics. It will reject all the neutrals and the photons. And we have the Q1, which is fixed at the analyte of interest, at the MBE of the analyte of interest. So only that particular ion will leave this Q1 to Q2. This is the collision reaction cell, where we can reject the analyte, interferent, using a kinetic energy discrimination process using helium, or a reaction chemistry can be adopted using the reactive gases like hydrogen, oxygen, ammonia, etc. So either we can take the analyte to the next level by en masse or mass shift process. This is the electron multiplier, which is the detector. And just see, this is how the triple quad selects the ions. So initially, this is our analyte, arsenic 75. Now we have set the Q1 at MBZ 75. And then all the other MBEs are rejected here itself. All the 75s will go to the Q2. Here we are admitting oxygen to convert our analyte into MBE 91. Okay, now our analyte is no more AS, it is ASO plus. It is an MBE 91. So the Q3 will only select this AS 91. Rest of the ions are rejected here. So this is how it is very useful in selecting the particular species. That is why this is very widely employed for speciation, because of this capacity. So this is our ICP-MS lab. This is triple quad ICP-MS. This is Thermodynamics ICS 5000. This is our triple quad mission. The LA is yet to be installed. It is in progress. Select the most appropriate element.
Ma'am?
Hello?
Yes,
Hello,
ma'am.
sir. Yeah.
Yes, ma'am. Thank you. That's a wonderful session.
Yeah.
Thank you for your time spent.
Yeah,
And
I will definitely reply this questions. They have posted some questions here.
yes, ma'am.
How do you select the most appropriate calibration curve, as there are some different types of calibration curves? Actually, these calibration curves are based on polynomial equations. And in the ancient equipment, they restricted it to just first 2 degrees. Now it is up to 5 to 6 orders. We can even add more calibration equations like it is called chemometry, addition of mathematical processes to measurements. So that is a separate research actually. Currently, we are using whatever is there in the software, but we can improvise on that by adding higher degree polynomial equations. So I take this opportunity to invite all the participants to visit SAFE physically, and they can also have a glimpse of our website, safe.iitm.ac.in. A wealth of information is given under one roof. We have around 20 highly sophisticated instruments, and with all the specs, model, and then detailed applications which are possible through each equipment is given in very explicit manner.
And ma'am, there is one more question, ma'am.
Yes.
Ma'am, I am working on membranes. Can you please tell me which equipment I can use with combination of ICP for correction of membrane?
Combination
Get more information on membrane faults.
Membranes and membrane faults. Okay. Actually, this ICP-MS we can use for many analysis, but ultimately when you're feeding in the ICP-MS instrument, it will be a destructive procedure only. You have to dissolve your sample. So if they really don't want to lose their samples, they cannot resort to this technique. It is a destructive method, ICP-MS. We prepare either the solutions in the aqueous form or organic form, or it will be dissolved in HF or an organic solution, and then it will be nebulized, and then ultimately it is converted into the ions. So if they really don't want to lose their sample, then ICP-MS will not be a correct method, I think. It is a destructive technique. Even OES is a destructive technique. MS is also a destructive technique. Only thing, the advantage of MS is it can be coupled with ion chromatograph and then HPLC or laser ablation. For laser ablation is mainly used to study the materials which are highly insoluble. And ion chromatograph, of course, we can do a standalone ion chromatograph separation for cations and anions. And of course, we have, if we procure the columns, we have procured columns for iron, chromium, mercury, and arsenic. At present, we can do the speciation of only these four elements, whether it is organic mercury or inorganic mercury, chromium 3 or chromium 6, or arsenic species, and of course, iron, Fe2 and Fe3.
Okay, ma'am. Thank you very much for a wonderful session, ma'am.
Thank you, sir.
Thank you, ma'am.
Thank you.
Dear participants, the next session will be demo experiment that will be sharply started by 10 to 15 minutes, another 10 to 15 minutes. Thank you. Dear participants, now we have a demo on FTIR Raman spectroscopy.
So, good evening to all. Myself, Dr. Venkatesh, Assistant Professor Research from Center for Nanoscience and Nanotechnology. So, this session you are going to see the demonstration of Raman spectrophotometer. So, before going into that, I just want to mention that the instrument which we have is nothing but the Renisha Invia Reflex Raman spectrophotometer. So, where a microscope is being equipped with the spectrophotometer. And so before going into the instrumentation, I just want to touch upon the simple basics for the Raman spectrophotometer. So you all know that when an electromagnetic radiation hits onto the sample, so there are several ways that it can interact, the light can interact with the sample. So it can absorb the light, it can emit the light. So in that way, the light can also be scattered by the molecules. So in this kind of scattering, so we have two types. So one is the elastic scattering and the other one is the inelastic scattering. So if the energy of the incident laser, that is the source which we are using for the Raman spectroscopy, and so when the energy of the incident laser and the energy of the scattered laser is same, then that is none other than the elastic scattering, or the other name is also called as the Rayleigh scattering. So when the energy of the incident laser and the energy of the scattered laser is being different, so whether it can be a more or it can be a less, so depending upon the difference, so we have the two different lines that is called as the Raman lines. So when the energy is lesser than the incident laser, then it is called as the Stokes lines, and when the energy is more than the incident laser, then that is anti-Stokes lines. So, but what we are detecting in the instrument is nothing but only the Stokes lines, which means the energy of the scattered laser is lesser than the incident laser. So we have an anti-Stokes filter, and before that we have a Rayleigh filter. So that means the Rayleigh lines will be filtered off, and followed by we have a anti-Stokes filter, and it finally it reaches the detector is nothing but the Stokes lines. So and you all know that the IR is an absorption spectroscopy, but whereas in the Raman the light is being scattered. So please please remember this. So this is a very basic, and in order to attain the conditions, so for IR spectroscopy it is nothing but the change in the dipole moment, whereas the condition for the Raman spectroscopy is the change in polarizability. So polarizability is nothing but the induced dipole moment. So whenever the some of them might have heard that the mutual exclusion principle. So those modes which are IR, the vibrational modes, so which are IR inactive will be the Raman active modes. So that vice versa is also possible. So in that case, the Raman spectroscopy is very useful in order to deduce the structure of the molecules by the vibrational modes of the functional groups. So going into the instrumentation part, so we have the first and foremost is the light source. So whereas here we are using the laser source. One is 532 nanometer and the other one is 785 nanometer laser. So you all know that the visible region covers in between the 400 nanometer to 800 nanometer. So we have 532 nanometer laser which falls in the green color, green region. So people used to call this as a green laser also. The other one laser is 785 nanometer which is nearer to the red. So it is a red laser. So we have a green laser and a red laser. So these two lasers, that is diode pump solid state lasers. We used to call it as a DPSS laser. So the laser has been generated and then the laser is being directed by the several optics present in the spectrophotometer and it reaches the Rayleigh filter and then it goes to the microscope. So in the focus. So here, this is the microscope. As I told, a microscope is equipped with the spectrophotometer and we have the different objectives. So starting from 5x, 20x, 50x and then 100x. So these objectives, it is like just nothing like magnification. So from low magnification to high magnification. So by this help of objectives, you can weave the sample and then you can weave and then the laser is being directed onto the particular particle and then you can collect the information. So that is the added advantage in the micro Raman, or the other name is also like confocal Raman. So both are same. So apart from after the objectives, so the scattered light gets collected by the objectives and then it goes to the Rayleigh filter. After that, because you know that the scattering is having Rayleigh scattering as well as the Raman scattering. So the Rayleigh scattering will be filtered off and then it moves to the slit, and after the slit it goes to the gratings. So for 532 nanometer we have a 2400 lines per mm gratings and then it goes to the anti-Stokes filter and finally the Stokes lines only will reach us this CCD detector. So what we are getting the spectrum is nothing but the Stokes lines. So when the Stokes lines will be present when the energy of the incident laser is lesser than the energy of the scattered laser. So now we have talked upon based on the energy. So coming to the wavelength, so you people know that the wavelength and energy relation where it is inversely proportional. So if you choose a 532 nanometer laser, so if the 532 nanometer is exactly like in the detector, it is 532 nanometer, then there is no peaks, there is no shifts. So that means the energy is no change in the energy. But if 532 nanometer is being shifted to 542 nanometer approximately, so I'm just telling the values for understanding. So there is a 10 nanometer shift in the wavelength of the laser which is used. So that 10 nanometer, what it indicates that, so due to the vibrations of the bonds present in your molecule, the energy is being shifted. That means, the wavelength is shifted. So this 10 nanometer, one nanometer shift is approximately equal to 30 centimeter inverse. So please note down this. 1 nanometer shift is approximately equal to 30 centimeter inverse. Since you all know that the x-axis in the Raman spectrum is the Raman shift. So the Raman shift is calculated from the wavelength using the certain formulas. So which means that 1 nanometer shift is equal to approximately 30 centimeter inverse. So if the incident laser, that means the green laser, is being shifted to 542 nanometer, then so 10 nanometer, therefore, you know, approximately 300 centimeter inverse Raman shift, because 1 nanometer is equal to 30 centimeter inverse. So in that case, so 300 centimeter inverse. What it meaning is, it means that you have to get a peak at 300 centimeter inverse if you have a 10 nanometer shift. So this is what, you know, the wavelength and energy relation, because the wavelength shifts to higher region. That's why I'm just telling you 532 to 542. So the wavelength is, it shifts to higher, so therefore the energy is being lesser. So I told that the energy, if it is a less energy, then that is nothing but Stokes lines. So and that means the energy is lost. So how the energy is lost? You all know that you know, when the laser light is being interacted onto the sample, the molecule can excite from the ground state vibrational level to the excited state vibrational level. So you are supplying the energy just to have only the vibrational transitions and not the electronic transitions. So if you are giving more energy like UV radiations, then there is a possibility for electronic transitions. That means ground state electronic level to the excited state electronic level. But you are providing the energy, only the sufficient energy in order to have the ground state vibrational level to the excited state vibrational level. So you know that the excited state lifetime is very short, so it has to come back to the original position. So if it comes with ground state vibrational level without losing any energy or without gaining any energy, so that is Rayleigh scattering. But if it gains some energy when it comes back to the ground state vibrational level, that is actually anti-Stokes line. But if loses some energy, then it is Stokes lines. So that and that lost energy only we are able to get the information, that is none other than the Stokes lines. So like, sir, wait, you explain for me. Say okay. So okay. So I will try to show the spectrophotometer. Five minutes. This full. So we have two laser sources and the laser is being generated, and so it is being, you know, it is being like traveled through this pathway with the several beam optics present here. So it is like a pathway, road map, like that. We can also call it as the road map. So the laser is being directed to the filters via several beam alignments, and this optical alignment is very, very important in every Raman instrument. So if there is a small changes in the direction, then you won't get the laser source onto the sample. So this is very important pathway, and from here it is being directed to the Rayleigh filters. So each one, like we have a 2 Rayleigh filters. So one for 532 nanometer and one for 785 nanometer. So actually right now in the software it is selected as 532 nanometer. So after this, the laser is goes to the microscope. So where we will be placing our sample for the analysis. So from here, again, the scattered light is being collected by the objectives, and then it goes to the Rayleigh filter, and from here it moves to the slits. So the laser is coming in down way, and the scattered light is goes to the slit. So from the slit it moves to the gratings, and from here, anti-Stokes filters are present. So your anti-Stokes will be cut it off, and what finally reaches the detector is Stokes lines. So this is our spectrophotometer. Okay. So I'll close the door. So there is a sensor also. So if not properly closed, then it will not be, like the laser will not be directed. Laser will be directed, but software will not be given. So do connect. The sample. So, so right now I'm going to place a sample for the analysis. So here we are taking, actually we have taken an aluminum holder. So because aluminum has no active Raman modes, like Raman vibrational modes. So therefore we have taken the aluminum, and in this the sample is mounted. So this is nothing but the graphene oxide. So because nowadays carbon allotropes is being that research in the carbon allotropes is becoming more and more. Therefore we want to show a graphene oxide based sample for the Raman spectrum. So since Raman spectrum is one of the best technique to distinguish between the allotropes of carbon. Most of them are aware that if you want to distinguish between the graphite and the graphene, so then it is the best technique. And the recent days, so the microplastic research is also been it is booming. So in that case we can move on to the 785 nanometer. Why? Because the 785 nanometer, as the wavelength is more, therefore the energy is less. So for polymers or biosamples, we can go for 785 nanometer, which is having the energy lesser than that of the 532 nanometer. So now the sample is placed, and we are going to focus the sample. So it can be clearly seen here also in this software, which is Wire 5.5 software. So here we can view in this our sample. So that's why I told that the advantage for the micro Raman is, so we can view the sample, and then we can direct our laser onto the particular spot, and then we can get the informations. So now we are moving on to the other objectives. So this is 20x and this is 50x. So most of the cases for powder samples, we need to stop at 50x because the 100x will be very closer to the sample. So there is a chances of contamination. So therefore, mostly what we will do is like we will stop at 50x for powder samples. In case of thin film samples, we used to go the up to 100x. That is the maximum objective. So we will go to 100x for thin films. So for powder samples, we will be stopping at 50x. So that will be sufficient to collect the Raman spectrum. So here we are focusing it. So this is the focused sample. So in order to view, we can increase the brightness. Now you can clearly see the sample particles. So from 5x, that means low magnified to little bit of high magnification. So now the sample is being focused. So after that, we need to set origin, and then so now we have to switch on laser, but actually already laser is switched on. So we need to calibrate. For calibration, so we need to click this icon, and then we have two templates. So one for 532 nanometer and another one for 785 nanometer. So since here you can clearly see that 532 nanometer is selected, and accordingly the grating is selected like 2400 lines. So if we select 785, then we need to go for the 1200 lines grating. So this is the selection for the lasers. So mostly for metal oxides, metal nitrides, metal carbides. So those kind of samples we can take this analysis in the 532 nanometer. But as I told, like for polymer samples or some bio samples, then we need to go for the less energy laser, that is 785 nanometer. So now the laser is being selected, and as I told, calibration for 532 nanometer. So, sorry for the technical issue. And so here, you can see the calibrated peak like the 520.5 centimeter inverse. So we have a single peak at 520.5 centimeter inverse. So it is clearly indicating that our laser is working very fine. So we can go for the analysis. So for analysis, so we need to go like for this arrow mark and then spectral acquisition. And there are two modes, static and extended mode. So we can go for the extended range. So if we know the like certain peak positions, then we can go for the static mode. So otherwise, generally we will go for the extended mode. So in extended mode, there is 100 centimeter inverse to 3200 centimeter inverse. So maximum value that we can go, the Raman shift is 3500 centimeter inverse. And the low that we can go is 50 centimeter inverse. So some of them will have peaks at around 60 or 70 centimeter inverse. So in that case, that low will be helpful. So 100 to 3200 centimeter inverse, that is the Raman shift. And this is the two important parameters where exposure time and the laser power. So the choosing of laser power and the exposure time is very critical for each and every samples. So for these carbon based samples, like most of them in our instrument, so we have been like chosen for 5% of laser power and then the exposure time of around 20 to 25 seconds. So in these ideal conditions, we will get good peaks. So, but for some of the samples, we need to go for the lesser laser power. So, which means the 100% of the laser power for 532 nanometer is 50 milliwatts actually. For 785 nanometer, it is 300 milliwatts. So in that case, like 50 milliwatts, so 100% is more energetic. Therefore, we need to come down to the very lesser percentage. If we get any peaks, then we can slowly increase the percentage in order to get the highly resolved peaks. So, so these two are critical parameters. So we are just applying and then we are running the spectra. Laser. So I'm just clicking here. So you can view that laser is the green laser is being interacted onto the sample. I hope everyone are visible. So that means now the laser is being whatever I told you, it is directed to the microscope and then scattering is happening. So the scattered light again collected back by the objectives and it goes to the detector via several filters. Then Stokes lines only it reaches the detector. Okay. So now the spectrum is running. So whenever you get the peaks, it indicates that there is a shift in the wavelength. So that is nothing but Stokes shift. So in order for the this graphene oxide, so most probably you will get the two major bands. So one is the G band, that is graphitic band. So now whatever you are getting the peak you are seeing is the G band. Then the another peak will be present. So that is the D band. So usually it is a defect band or a disorder band. So these two bands and the relative ratio will tell you that whether it is a graphene oxide or it is other forms. Like for example, this will be very useful for identifying the graphene oxide or reduced graphene oxide. So this you are getting like the vibrations of the carbon double bond carbon atoms, that is sp2 hybridized carbon atoms. So what I'm trying to tell you is that so this is nothing but so it is a vibrational spectroscopy. So even though the FTIR is also the vibrational spectroscopy, but for getting the peaks for allotropes of carbon, so the Raman spectroscopy is best technique. So that's why we have chosen particularly a carbon-based compounds for the demonstration purpose. So this is the raw spectrum and spectrum. Okay. So this is the raw spectra. So now this spectra actually we will process little bit. So tools, subtract baseline, and then we'll go for slight smoothing of the spectra. So this is how we will give the data. So you have this background subtracted and slightly smoothened data as the XY files. So after getting this data, you can plot in the origin software, which everyone knows very well, most of the persons. So then we can pick peak positions. It will get you that what values are where peaks are presented, where positions. So for example, here it is 1596 and 1347. So like this, you can run for several samples, metal oxide samples, polymer samples. So for polymer samples, like as I told, we need to shift to the 785 nanometer most of the cases. So that time, you will get a n number of peaks, because various functional groups will be present in several polymers. So you will get different peaks. So this is about the spectral acquisition. So in addition to that, we have the mapping also. So this is a normal spectral acquisition. So we have here the map image acquisition, which is like we can do the point mapping, line mapping, as well as the area mapping. So like if you select some points in this, in this spot, in this image, and or you can draw a line, or you can select some area, then you can run the spectra, but it will take a longer time. So for example, if you do a point mapping, it will take some 30, depending upon the points, number of points, it will take 30 minutes to 1 hour for one sample. So, but if you go for the line mapping and area mapping, so for line mapping, it will take half a day, and for area mapping, like 1 day per one sample. So that is a very time consuming process. So whenever it is required, so we will go for that. So otherwise, like we will do the normal spectral acquisition. So moreover, we have the additional high temperature Raman setup. So that is called the Lincoln hot stage. So in this one, like simultaneously you can heat the sample, and simultaneously you can record the Raman spectra. So this particular feature is helpful in order to study the phase change behavior, or like mostly it is phase change behavior of materials, or up to which temperature your material is being stable. So those kind of studies will be can be analyzed, and so the important requirement is 0.8 mm dia samples. So that is the only critical thing in this particular thing. So if we like mostly we will prefer 0.8 mm dia of the in the form of a pellets. So if you have a film also, like if you have a film also, 0.8 mm will be will be sufficient to place the sample. So like every intervals also you can study, like intervals of 50 degrees Celsius, 25 degrees Celsius. So again, it's also a time consuming process. So it will take like 1 day for this one sample. But you can get the more and more information when it is exposed to the temperature. So how it is happening with respect to temperature. And so these are all the various features for this Raman spectroscopy. So if you have any clarifications, then I'm ready to answer.
Participants can ask questions.
Or you can post the comment in the chat box. That is ready to answer for your question.
Okay.
So if not any question, then I close the session. Thank you, Dr. Venkatesh, for giving a nice and wonderful lecture and the basics of the Raman. Thank you.
Thank you. Thank you. Thank you to all the participants. Thank you very much.
No queries. Okay, fine, ma'am. Thank you.
Okay.
Means that Sarah has to very clear. Crystal clear.
2 minutes.
Okay, participant just hold under 5 minutes. The next session will be on. Wait. Take it. Thank you.
Subhenjit Rasra, sir, Associate Professor, so Center for Nanoscience and Nanoscience Technology, Satyabama Institute of Science and Technology. So today we are going to discussing about the surface area analyzer. Generally, people used to call this is a BET instrument. So by the name itself, we can come to know like a BET surface area analyzer. So this instrument is only going to talking about the like surface area analysis of the material. So, like, what are the possible materials we can analyze the samples, like powder samples, pellet samples. So, thin film samples also it is possible to get the surface area measurements. So, what is the advantages of the BET instruments then compared to other models? So, initially, so early century people they have developed like a Landmuir model as well as like Freundlich models also people they have done. So in the in that proposed model, so what has happened is like so that material has that proposed method has like more disadvantages over like BET instruments. So in that, what are the disadvantages and what is the advantages of the BET instruments? So in the disadvantages, it is a homogeneous like absorption only. It was happened in the like Freundlich and Langmuir. So, but heterogeneous also it is happening in the Langmuir. But here we can do like a multi-layer adsorption process. So it is like a biggest advantages of this like BET instruments. So like you can't calculate the surface area like accurately. So it is like a ISO standard, like people also standardized instrument. BET is one of the instrument here. So here we are having an instrument. So we will come from like a basics. So what is adsorptions? So adsorption is nothing but like a you know adsorptions. So adhesion of atom or molecule on the surface of the adsorbent. So there is a adsorptions. So you know absorption is different, adsorption is different. So what can we say? Like so adsorption means like your atoms or molecule, like adsorbate molecule. So what is adsorbate here? So nitrogen will be your adsorbate molecule. So that nitrogen molecule will adsorb onto the adsorbent. So adsorbent is nothing but your material, so your synthesized material. So here like Langmuir and Freundlich, it was only talking about the non-porous material. But here we can talking about the mesoporous material, carbon black, zeolites. So non-porous materials and capillary, like whatever the materials you are preparing, so that we can check it. So except for the liquid samples. So liquid sample we can't do because like there is no pores or anything is there. Like here we can do the BGS desorption method. So from that onwards you can come to know like how much pore size, your pore volume are there in your material, so that we can check it. So then slowly we will come to the like instrumentation sections, like what we are having. So by after getting the points of like your like data, so you can you can do the you can do what can I say? So based on the hysteresis, you can calculate like what kind of graph you are getting from the hysteresis. Like we initially what will happen, like before starting of the like analysis, so you will get the like after analysis you will get like a graph like a monolayer adsorption. So after that it will go for the like multi-layer. So some other cases multi-layer it will start before the before the unilayer formation. So that also it could be Anton bar look it into this, like we are having a four stations are there. So this is The pellet sample regarding like so sodium pellet kind of, otherwise like fenugreek, no, so kind of samples also it could be analyzed. Then powder samples like a fine powder sample, and thin film samples like thin film samples. I don't have an example right now, so that also it could be done here. Okay, so after finishing degassing, you have to weigh the sample again. So because if you are like keeping the sample for degassing 100 mg, in case like after degassing your sample might be reduced to 80 mg, which means that 20 mg of your sample might be your contaminant after putting like degassing. So for degassing, your temperature it should be like a sufficient. Like if you are like giving a more temperature than your sample sustainable temperature, so it will start to melt. So we can't do anything. Your sample it will be like a wasted only. So for that, before that you have to do the TGA. TGA is nothing but a thermal gravimetric analysis you have to do. So like that temperature, when your material is like stable, like I am synthesizing some metal oxide sample, so it might be stable up to like 200 to 300, or like 300 to 400, 500, 600. So you have to fix the time like a temperature. So that temperature only you have to keep it here. Like some materials like polymer materials, it may degrade around 80 degrees centigrade. So we have to give the temperature for how much we can give, like a 50 degrees centigrade only. So that material can sustainable for some temperature. So that temperature only we have to give. So if you are going beyond that the level, so your sample can be like molten condition only. So we can't do anything. So once after weighing the sample, we have to transfer the sample to the analysis chamber. Here we are having the analysis cell 1, cell 2 we are having. So here we are having a cell 1 and cell 2. So here this is a coolant sensor, this is a relative pressure, P0 sensor, P0 sensor, like a saturation pressure it will sense. Like this one is a coolant sensor, this is the liquid nitrogen. So you can know this is a liquid nitrogen Divar. So we used to keep it like this. So for degassing we used to do like a 2 to 3 hours, 3 to, it depends on your sample. If you are like thinking that your sample is contaminated more, then you have to do the more time for the degassing. So once the degassing completed, so we used to immediately transfer to the, we used to weigh the sample, then we directly transfer to the analysis chamber. So here like a helium gas it will be there. So to avoid the space, we used to put the glass rod into that. Like because we are taking a very small quantity of sample only, like 100 mg or 20 mg only we are taking. So it will become up to this much level only. So for that we are putting a glass rod into that to avoid the more space. So after that, what is happening here, like a helium gas, it will go into your sample. So it will measure the pores of the your material. So how much pores, like your dead space, like how much spaces are there to available for the nitrogen absorption. So that it will helium gas it will measure. Okay, so here we have to load the sample, like sample 1, sample 2. Like before loading samples, so here we have to enter the sample name, and so that and all I will show you here. So it won't be visible, I think. Visible aguma. Okay. So here we have to go here, outgassers. If you want to fix it, station 1. So there we have to go there and we have to fix it. For analysis also, we have to like edit parameters. What are the things we need to put? It is a powder sample or like a fine powder sample or thin film sample. So what is the dimension of the cell? Because 6 mm also we are using, 12 mm also we are using. For thin film samples, we are having a 12 mm, 9 mm like sample cell also we are having. So those things we have to mention here. Okay, so how many points of adsorption we want? So desorption, how many points we want? So those things we have to, everything we have to mention here. So once everything is fixed, we have to give the start analysis, because for that here I didn't load any samples, because each sample it will take more than 16 hours it will take for the if you are keeping for degassing for 2 hours, anyways it will take more than 2, 3, 4 hours it will take, because once it will optimize, then backfilling it will be there. Whatever the helium gas is purged, then it will like backfilling it will be there. Okay, so the it will take 3 to 4 hours time to finish the degassing. So once we are transferred to the analysis chamber, so like it will take a more time to optimization, because like helium gas it will purge. So how much it is like a empty space it will read. Just okay. So that's why we are putting the glass rod into that. Okay. So then what is happening? So once the optimization is done, your this Divar it will start to go up. Okay. This jog it will go up. So once it is reaching the sample like this, so anyways your like sample should be depth in like 3 to 4 centimeters. Like this much depth sample it will be in the liquid nitrogen only. So once it is reaching in this level, this sensor it will sense. So here we are having a one light. So once it is reaching the liquid nitrogen, it will this light it will start to on. This light of the indication. So once it reaching the liquid nitrogen in this Divar, so it will show a like blue color light it will show. So that is the indication. Then the jog it will go up and down. Then it will be stable. Okay. So for throughout the analysis. So for the optimization, it will take more than 1 hour for 1 hour. Then again it will start to analysis, like one point it will come. Okay. So the helium gas, what is the role of helium gas? So because it is using as to measuring of the dead space in your molecule, which means that lot of pores will be there. So it will analyze and it will give it to the manifold. So this is the manifold. So it will create everything. Okay. So this much amount of pores are there. So accordingly it will release the nitrogen gas into it. Okay, sample. So it will release the nitrogen gas into it. Okay. So it will send the nitrogen. So it will like adsorption, it will takes place. So once the completion of adsorption, so desorption it will start to takes place. Okay. So this is the instrumentational techniques. So here this is a manifold basically it is like a readout things the brain and heart of this instrument. So without the manifold, it's like a on off switch. We no need to do anything. So only thing is that we have to load the sample. So we have to give the parameters and what can I say? We have to give the parameters. So once the degassing completed, so again we need to give the so what is the name of the files? So what shall I save? So everything it will ask. So that we have to give it here. Okay. So after weighing the sample, so we have to enter the weight after the degassing. So what is the weight of the sample? So those things accordingly it will calculate. Okay. So by so right now you just think it off. So we have done the we have analyzed the sample. So we are getting a graph like this. Okay. So based on the graph we can come to know whether my molecule, whether my material is showing like a mesoporous or macroporous or like a microporous material. Okay. So that you can come to know based on this hysteresis only. Okay. So right now I have given like a 40 points for the adsorption and 40 points for the desorption points. So here you can check it. This is the AD point. So in this point where which adsorption and desorption takes place at the same point. So firstly I'm just giving you one graph to you. So you will see only about the what is the x-axis and y-axis. Then you can come to know. So what is this graph, right? So this graph is plotting about the x-axis will be the relative pressure P by P naught value and versus the volume of gas, and that gas is nothing but the nitrogen. So molecule adsorb onto your adsorbent. Okay. So based on the things we can calculate the specific capacity what is called specific surface area and what will be the pore volume. So everything it could be calculated by this graph only. So this is a mesoporous material which we have synthesized in our lab. MCM41. Okay. So how to do the interpretation. So I'm just telling you. So your relative pressure it will be 0 to 1. Okay. So that is a relative pressure. We can't go beyond that the level. So if you are going beyond that level, what will happen? The capillary condensation it will happen. Whatever the gas it wanted to absorb, so it will be fully condensed onto your sample. So there will be no desorption, it won't occur. Okay. So that's it. Once the adsorption happened in the AD point, so it will start to come back to the desorption method. Okay. So this is the things it will happen. From the desorption, you can calculate the pore size distribution. So generally people used to call BJ-Gauge desorptions. Okay. BJ-Gauge method or pore size distribution people used to tell. Okay. So right now I'm just focused okay. So I'm just right click on it. So edit data that I'm just going. So to check it for pore size BET surface area. So this is an instrument. People are thinking that this instrument is only for the surface area. It's not only for surface area. For surface area, it's like a kind of one measurement only. Okay. So other than that also you can get it. So for surface area you can within a 4 point you can get it. So no need of adsorption and desorption points also. So here what we have to do to get the adsorption of you have a selected area. Okay. So for BET surface area you have to choose the point from 0.05 to 0.3. So where you can get the which is a point which you can get the surface area of your sample. Okay. So you have to just click this you have to click the values from 0.05 to 0.3. This is for the multi-point BET surface area. For single point BET surface area you have to select only 0.3 relative pressures only. So if you are choosing this you will get the surface area, single point B surface area as well as multi-point surface area. To get the top plot which means that T plot, people used to tell. T plot means we can calculate the micropore volume, okay, micropore area, or micropore volume or micropore external area. You can get it from the T plot. And Langmuir surface area also it is possible here. And one more thing is that for pore size distribution, you have to select the desorption points, like from 0.9 to and the desorption points you have to select it. So from the points you can get the pore size distribution. For pore volume, how you can do? So you can get it from the AD point. Okay, so you have to just click the AD point, then you can get it the pore volume of the materials. Okay, so these are the things you can do it here. So right now, so I have done, this is a pore volume, so I'm just click it. So this is a pore volume. So other things are like, so for the desorption, you have to select the point from the AD point to 0.025 of the relative pressure. Okay, so once you are selecting, that's it. So for Langmuir, it will be, so for Langmuir, we have to choose the points from the 0.05 to 0.3. For Langmuir. So simply you have to click the points. So whatever we want. For T plot also same, 0.15 to 0.4. So before that we have to know the points. So what is the points belongs to the area, like multi-point BET, single point BET, Langmuir point, and like a pore size distribution. Those point and all we need to know. So then and then we can give it, do for the analysis. So only thing is you have to select the points. So that's it. No need to do anything. So once the sample is to be properly mentioned, like your analysis is to be mentioned, so you will get the like data. So you no need to do in your laptop or anything. Like if you like, we will give the graph as well as like PDF also we used to give, and what is the surface area it came. So those things, everything we will give it to you. So you no need to do the calculations also. So what is the micropore volume? So what is the surface area? So how much pore size distribution it came? So everything. So by the graph itself, everything it will come with the along with the graph itself. Okay. So right now we can check it for the tables. I am going just BET. So multi-point BET. So how much it came? Like 863 meter square per gram it came for the multi-point BET. Okay. So for single point BET, so that also we can check it. For single point BET, so how much it is coming? Like 843, 842, 2.9, like a very 0.1% only, plus or minus only there. Okay, so it's not like, it's like a negligible variation is there, because this is single point. It will be talking about the only 1 point, 0.3 of the relative pressure. But in the multi point, so it will be from the 0.05 to 0.3. It should be noted down. Okay, so next thing is that to get the micropore volume. So what we have to do? So already we have chosen the T plot analysis. So only thing we have to go to VT method and T plot method micropore analysis. So how much it is coming? So micropore volume. Now micropore volume is nothing is there, because of it is like a mesoporous material. Nothing, micropore area, nothing is there. So we can't get it anything here. Okay. So that the external surface area 863 meter square per gram it is coming. So accordingly you can calculate everything. So one more thing is that area overall summary, that we can check it, area volume summary. So in the area volume summary, so like people are proposing, lot of people are proposing their method. So I am proposing one method. So one fellow is proposing one method and another fellow is proposing one method. Like kind of methods are there. See here, DH method, HK method, SF method, DFT method, BGH method. lot of methods are there. So this also you can be keep it in your data, like you can make one data table. So there you can mention the like other theorems, like other people are what they are telling. So and is corresponding surface area, what is the corresponding surface area, what they are and is corresponding pore volume data and pore size data, everything it can be listed in your paper. Okay, so these are the things you can do, like overall report also you can make it. So this is a Satyabama University. We are like charging only for the sample 1,500 only. So other university and all people are charging more than 2,500, nearly 2,500 to 3,000 people are charging. So if you really want to send the sample, you can send it to me. My name is Subhas, so you can send it here. Like you can get my number also in your group. Then like before sending the sample, you need to know the TGA temperature. So because this is like a very much important to do the analysis, and how many points you want. So like I hope you people you understand everything. Like a lot of people they are sending the sample without knowing the BET instrument also. I think you people might know about everything regarding the BET. So yeah, if it is any queries, you can ask me. Any questions? Like we are using the Quantachrome. Quantachrome Asquin is a software. So which is like a licensed people they won't give easily. So this is Anton Par, like a personal thing only. Quantachrome is the company. Anton Par. That is the software. So any other questions? So if you people are asking questions means the which means that you are understand something, like so I used to think. So what are the questions you are having? So you can ask, because I can't see your face and all. Uh, Vancha. Okay, then. So this is Subhas, another Subhas from fluorescence spectroscopy. So this time we are going to talking about the like of fluorescence. So how the fluorescence is forming. So what is fluorescence? Firstly, we have to know. So what is fluorescence? What is absorbance? So without having absorbance, we can't do the fluorescence. Okay. So this is the first point you need to know before sending the samples. So before doing the analysis wherever you are going. Okay. So what is absorbance? Like fluorescence is working under the principle of Jablonski diagram. So this is my PhD area. I am working on the fluorescence only. So we are synthesizing a lot of organic molecules and quantum dot molecules for the sensing applications. Okay. What we can, it is working under the principle of Jablonski diagram. Okay. So initially your molecule, so when we are giving the energy, okay, so it will go to the ground state to the excitation state. Okay. So in the excitation state, it's not like a permanent state. So it is like a kind of temporary state. Okay. So once it reaches lower singlet excited state to the like a ground state. Okay. So in the case of in the form of light, form of luminescence. Okay. So this is the fluorescence. Okay. So that what is happening? So if my molecule is going and exiting the molecule, my molecule is exiting and going to the S3, then what about the molecules is coming from S3 to S1? So those electron, it will be formed as like a in the cause in the form of dissipation of energy. Okay. So in the form of heat energy as collision energy. Okay. So from the S1 state to the ground state in the form of light. So this is like a fluorescence. So what is the phosphorescence? So molecule, so that electron is going to the excitation state S1, S2, S3 state. So that electron, it will going to the triplet state. Okay. The spin of the electron will change. So in just think about it. So in the ground state, initially electron, it will be like that, plus half, minus half, it will be 0. Okay. So when we are giving the energy, your molecule or electron, it will go to the excitation state. So without altering the spin of the electron. Okay. So it will be like a you know the spin multiplicity 2s plus 1, right? So the spin of the electron plus half and minus half, it will be 0. Then spin multiplicity will be, it will be 1 only. Okay. So when the electron is going to the triplet state, the spin of the electron will be changed. Okay. Then spin multiplicity, it will become like a 3. So that's why we are calling a triplet state. So triplet state is like a, then it will come to the lower triplet excited state to the ground state. So in the form of phosphorescence. So you just know, so fluorescence is a instantaneous process, phosphorescence is a like a non-instantaneous process. Okay. So if you are cut off the light, so immediately fluorescence it will stop. So phosphorescence is like a different case than fluorescence. Okay, so here what we can do, so here we can do like a liquid samples as well as solid samples as well as thin film samples also possible here. Okay, so possible here. So this is like overall things you have to know about the fluorescence. So for this is a cuvette. So this is like a transparent cuvette. Okay, this is a transparent cuvette. So once like in the UV, so you can see one side it will be opaque, one side it will be transparent. Okay, so here we have to keep your like you have to hold the cuvette by your at the edge of the cuvette only. So you should not keep the things like in the mirror part, transparent part, because your fingerprints also it may cause some like it may interfere in your fluorescence intensity. Okay, so before starting the instrument you have to switch off the light, and we have to ensure so whether the AC is turned on or turned off, because like because what is that that lamp should be because helium xenon lamp we are using, so it should be like in the cool place only. So we here this is the one switch. So this is a silica gel we are keeping inside of the holder. Okay, so to avoid the contaminants, so let it on for some time, so then it will come the run analysis. So this is the software we are having, so FL Solutions. So this is the instrument for fluorescence spectrophotometer, Hitachi F700. So this one we have purchased 2 years back. So once we are click on the software, so it will take some time. So for the initialization, so we have to wait for that. Before that, we have we can make the sample for the sample preparation to do the analysis liquid sample. For we will go for the solid sample, because solid holder only there inside. So so that's why I'm just going for the solid sample. So here you can see here. So this is the like a glass. So this is like a iron holder only. Okay. So inside you have to fill the sample. Like half F and half you have to send the sample. So because I can't tell the like some material it will be like a density less, some material it will be like a more density, because I can't tell that, because I can tell the like a how much you need to send, like a half F and half. In the 2 ml F and half, I'm not having anything. So in that this is like a 5 ml F and half. So you have to send the 1/4. You have to send the 1/4. So after loading the sample inside, you have to tight it gently. So you no need to tight more. So because you can't like get it back. Okay. So this is a samples. You have to ensure it. It should be free of contaminant. Everything I have loaded before itself. For cleaning purpose, I'm just using the acetone or IPA. Also, you can use it because I'm thinking that my fingerprints it might be there in the like edge of the mirror. So that's why I'm just simply wiping it. So this is a sample. So which we have synthesized. So once the software is ready, we can place the sample inside. So this is the light. So this is the light source. So this is the detector we are here. This is the for solid sample measurement. So we are using the sample holder. Okay, done. So we have to place it like this. So your that light source it will pass here, and the detector it will detect from this side. Okay, so it will be like a little bit tilted. Okay, for solid sample like a liquid sample, I will show you different one. Okay, so simply we have to close it. Yeah. Then we can come to the so what is this? So we can come to the software. So what we have to do? So before doing fluorescence, as I said, so we have to have a absorbance spectrum. So in the absorbance spectrum, I am getting the excitation. Maximum population is coming from 270 nanometer only, as I observed in my UV spectrum. So that's why I'm going for the solid sample. So we have to go to the instruments. So initially we have to fix the range of the fluorescence spectrum. Okay, so how we can fix it? Okay, so for that, what we have to do? So if I'm exciting the molecule X, okay, so my starting wavelength, it will start from X plus 20. So in case I am telling that right now I am exciting my molecule 300, then my starting wavelength, it will be 320. Okay, X plus 20, 320. Okay, then after that, if I am starting the I have to end up the spectrum also. So it will be from like X into 2 minus 20. 300 means 300 into 2, 600 minus 20. Okay, so it will be 600, 580 only I have to give. Okay, so as you know, as I know, my sample is exciting around 270. So that's why I am keeping 270 as the excitation, and the excitation starting wavelength, it will be X plus 20, right? Then 270 plus 20, 290. Then the 270 into 2, the ending wavelength, it will be 540. 540 minus 20, it will be 520. Okay, so this is the range we have to fix like this. Okay, so once we are fixing the things, we have to select OK. So somebody they are doing, so if you people are not getting the intensity proper, so you can give the 10 nanometer slit also possible here. Okay, so after selecting everything, so you have to ensure the sample name. So right now I am putting the sample name, solid sample. So this is online section. Okay, na? So that's why WIAM online means on. Okay, EX at 270 we are exiting the nanometer. Okay, so so before doing the analysis, I have to tell you one thing, like you are doing the absorbance spectrum. So what you are getting, so your x-axis will be wavelength and the y-axis will be the absorbance. In the case of fluorescence, this is the wavelength, x-axis will be wavelength and the y-axis will be the fluorescence intensity. Okay, some people they used to call photoluminescence. Okay, then we have to choose the file name as well as the where you have to destination, so where you are going to save the whole files. Okay, so then already we have chosen the file Vim 2025, so just click it OK, then just OK only. Okay, then everything is ready for the analysis. Only thing is you have to keep the sample and fix this window. That's it, no need to do anything. Then firstly we went to like a method section, then sample section, then measure section. If you are clicking measure, it will start to measure. Okay, so here you can see everything, it will be everything it will be there, like what is the excitation which we have given. So what is the emission is like, right now present emission wavelength. So everything it will be here. See, you can see like right now peak is coming. So which means that your molecule is getting the fluorescence around this particular range. So here one more thing is that we can do the reverse excitation also possible to confirm the your material which it has shown the correct way, whether it is shown the correct excitation or no in the your UV visible spectroscopy. So that we can check it from the emission spectrum. Okay, so that could be possible here. So what we have to do, so we have to check it here, and what is the maximum emission we are getting, around 440 nanometer only. So so we given the excitation and we are getting the emission, right? So right now what I am doing, so we are giving the emission, we are getting back the excitation. So to ensure it, okay, so instrument I am just going, so instead of emission scan mode na, so instead of emission I am just going excitation. Okay, so excitation means I am getting the excitation around 440. So for that also we need to fix the range. So how we can do it? So excitation starting wavelength it will be, so some rule are there na, as I said. So excitation starting wavelength it will be x divided by 2. So 440 means x divided by 2 means 220 plus 20. Okay, then 220 plus 20 means 240. Sorry, 240. Starting wavelength will be 240. So ending wavelength, it will be emission, whatever we are getting the emission minus 20. Okay. So at the last, I will ask you one questions, like I am fixing the one window. Okay. Some people, you people should ask this question, then I will answer. Okay. Okay. Then 440. So we fix this range. So why we have to fix? Like somebody, you people should ask this question, then I will answer in this questions. Okay. So right now we are giving the emission and going to get the excitation. So for that I need to give the values now. So emission at 440 nanometer. That's it. So sample should be identified. So that's why I'm giving the different names. So I'm just giving the okay. So once we are fixing the destination, then no need to do for the other times. So only thing is you need to change the sample name. Then we have to give the measure, because you can see from it is starting from 240 to 420 what I mentioned. So here you can check it. So what is the excitation your molecule is following? So whether it whether it is showing a correct excitation what you are getting in the UV visible spectroscopy. So that you can check it from here. So excitation is nothing but your molecule is like absorbing, so this particular region your molecule is absorbing more and more. Okay, so that is the excitation. So here also some peaks are peak is coming. Okay, so but it is not much like higher intensity. Okay, compared to this one. So that's why we used to giving more excitation around like a 270 nanometer. So here you can check it. See, this is the excitation spectrum. This is the your emission. Okay, so your emission is coming around 440, and the excitation is starting from 270. Okay, so this is the things you need to follow. Okay, so this is for the solid sample. So I am going to load for the liquid sample. So that too you can see visibly fluorescence. So right now you can check it, because like this is online mode, na? So camera it can't go inside. So because this is a solid sample, you can check the fluorescence. Okay. Okay. So here there is a integrating sphere spectrometer, how the results vary for solid and liquid and semi-liquid sample. Yeah, for liquid samples, it will be like so we have synthesized a zinc oxide sample. So initially, so it has shown a more intensity. So when you are coming to the liquid samples, so your concentration it will be comes into the concentration. So semi-liquid also it will be different only. So when you are coming into like liquid sample, so it will be like a concentration based. Okay, so sir. So here, yeah, but temperature dependent data are there, but this is the instrument is not applicable for the temperature dependent data. Okay. So those this is like some interesting questions, like temperature dependent studies we are not having. For that we have to purchase like external things. Okay, to do the analysis of the temperature studies. So for here we have to fix the external addition of the instrument. So that we can use it for the further characterizations of the PL studies. So this is for the liquid studies. Okay. So generally it will be like that only. So we have to keep the cuvette, it will be like that. So your light it will pass through here, your detector it will detect from this side. Okay. So another questions, one more question is, please parameters we can extract from PL data rather than emission, and what parameter we can extract from PL data rather than emission? Excitation wavelength, please. Excitation wavelength, generally like we so it is like a single excitation, right? So you people should give the data excitation wavelength from your absorbance only. Okay, so excitation here we can't do everything. So your molecule may excite around like a 270 nanometer. Okay, but we don't know about it. So we will give like a 271, because here excitation wavelength is fixed things. So we can't change it like a 271, 270. We can change it, but so the range of excitation is like a very broad. So how we can do the like excitation from 271, 272, 273, 275? We can't do those things. So now, so for that you have to give like some approximate data, like from your, if you are not doing the things for the absorbance of your spectra, so you can give it as like you can tell like from the literature, I have synthesized this sample, so is showing the similar response, and this molecule might be giving the excitation is around 300 to 320. So if you are giving this range, so I can somehow I can manage it. So because for one samples I can't do like more than 10 readings, na? So better you should do fluorescence also. Okay, so from the emission spectra, emission and photoluminescence, so both are like same only. So some people are thinking photoluminescence is different, fluorescence is different. Okay, so both are like same only. So here what kind of application we can do, for my sensor studies we have to do like a different excitation. So which excitation is like a maximum is showing, and different solvent studies, like in the solvent studies what is happening when we are increasing the polarity. Okay, when we are increasing the polarity, so what will happen, your absorbance peak, it will shift to the blue region. Okay, so it will like it won't be blue region, so it will be as a blue shift. Okay, then when we are increasing the polarity, in the case of fluorescence it will be a red shift. Okay, so that also you can find out in things. For most of the nanomaterial it will be dissolved in only in the water medium only. So quantum related studies, so that you can get it from the PL data. So temperature dependent studies you can do. Then PG studies, for sensor studies, selectivity studies, anyways you have to do. Then what is the LOD? Then real sample analysis. Lot of variety of applications are there. Then reusability, reusability of the sensor. Some people are doing the LOD, what's called LED applications. So that also it could be possible in the fluorescence spectra. Okay, then slowly I will move to the like liquid samples. மறுபடியும் கொஸ்டினா இது நான் ப்ளேஸ் பண்ணிக்கிறேன். So band gap, yeah, band gap we can calculate it from using like absorbance and fluorescence also. It could be possible. So from PL as transfer emission wavelength to energy. So can we extract energy band gap from PL as transfer emission wavelength to energy? Actually, I am not understanding this question. So but band gap analysis you can get it from here. Like you have to take the band gap, you can do it from alone in the absorbance also. So you can do it here also, but I didn't try anything band gap analysis here. So because we are working on the like organic materials only, we are not doing. So for the nanomaterial, so we have did the band gap calculation from top plot using the absorbance spectra. Okay. Okay, so this is a pivot. So firstly, what we have to do, we have to get rid of the contaminants. What I'm doing, so before loading the samples, so I have to wash with the either IPA or acetone. Okay, to remove the contaminated in the sample. So if it is small contaminant also, liquid is especially liquid. If it is any contaminants are there, you may get like lot of impurities in your samples. So this is the molecule which I have synthesized. This is synthesized. This is the quinoxidine sample. So we have to wipe with the acetone also with the tissue paper. So because my fingerprint also might be might show some like if it may reduce the intensity. Okay, so it may reduce the intensity or it may enhance the intensity. So this is just the molecule I have synthesized. We should not expose to the light. Okay, so otherwise both photo bleaching, everything it will occur. The DMSOA. Yeah. So when we are like in the solid sample, when we are like so this is like a more concentration sample. Okay. So when we are like giving a less concentration of the sample, so so your molecule can easily every molecule it can easily go to the excitation state, it can come back. Okay. So if I am giving like a coagulation sample, like a coagulation medium, okay, so some of the molecule can only can go to the excitation. So the molecule it can pass to the next molecule, okay, for the coagulation medium. So that's why we have to give like a small concentration is sufficient for the analysis. So I'm just keeping the sample here. So this is the molecule. I got the excitation around 360 nanometer. So right now you can see the fluorescence, right? Yeah. So this is the fluorescence. So my which means that my molecule is like exiting mostly around like a 360 nanometer. So which I got from the UV visible spectroscopy. Okay. So before after synthesizing of molecule, so you have to do the UV visible spectroscopy. Okay. So that spectra you need to have first. So this is emission. So to get the like to fix the range. So as I said, so I did the fluorescence like UV visible spectroscopy. I am getting the molecule more in the region of 360 nanometer. So 3 plus 20, 360 plus 20, 380. Then the ending wavelength will be x into 2 minus 20, 700 nanometer. Okay. So excitation limit and the emission split which will be 5 only. I am just keeping. Okay. Then everything it will be like a same only. We no need to change anything. Okay, once we are giving okay, then sample name. So this is like a liquid sample. So this is a quinoxalin based molecule, liquid. So excitation at 360 nanometer. Just I am copying this one and paste it here. Okay, just okay. Then measure. So we are getting the color green region, which means that we have to get the peak around like a 500 range only. Okay, so this 500 range is the like possible for the like a green region. Okay, so if it is like a 300, so we used to get the spectrum for the spectrum like what can I say? It will be in the blue region. See, it is coming, the peak is around like a 500 nanometer, around 500 nanometer. So 498. So here also we can do the reverse excitation, so it is possible. So I will ask you. So I'm just one more thing. I will tell you. So why we are fixing this range, because of your if you are going beyond that the level. So what I told you, like we have to fix the starting wavelength and ending wavelength. Okay. So if you are going beyond that the level, your Doppler peak it will arise. So whatever you are getting the excitation spectrum, like a same spectrum you will get in the emission also. If you are going beyond that the level. So that's why we should keep this range alone. Okay. So okay. So I'm getting the excitation is around 360 as I said. So my emission is around like 495 or 98, like approximately 500 na. Okay, then method we have to go instrument, then instead of emission we have to go to the excitation. So my emission wavelength what it came, so 500 nanometer. So 500 divided by 2, 225, 250 plus 20, 270, 270, then 500 minus 20, 480. Okay, done. So right now we are giving the emission, we are getting back the excitation. So it is possible here, but without knowing excitation, we won't take back the we won't take the sample for the analysis, because we can't give the every values, every readings. Okay, so because it's like a broad range, like a 200 to 900. So how we can give the excitations? So it is not possible for us. Okay. So here we are getting the emission at 500 nanometer. Okay, then measure. Tani. So actually, I got in the spectra also same spectra only I got, but my molecule is effectively it like increasing, absorbing most of the light in the 360 region only. So that only we are getting more and more here. Okay. So this is the confirmation of the excitation of the spectrum. Okay. So this is the things we need to do. So this is like a simple things you can do. If you have any other queries, so that also like some other people also asking TCS PCS. So TCS PCS is nothing but the like single time correlated single photon counting. So that facility also we are not having. So this is the instrument. It is like a 20 lakhs rupees. In the BET, so that is like a 60 lakhs rupees. Okay, so this is the instrument we have purchased last 2 years back. We purchased. Yeah. So we are moving forward to looking forward to have a like a other facilities also linked with the fluorescence spectroscopy. I hope that next upcoming period, so we may get the TCS PCS and like a term, as you said, the time dependent peer studies. So it will be possible here. Muna. Okay. Yeah, is there a direct method to get a quantum yield? Yeah, so this is a direct method to get the quantum yield. So you firstly you have to know what is quantum yield. So number of molecules emitted by the number of molecule absorbed. Okay, so what we have to do, so to get the quantum yield, you have to have a absorbance spectrum of the different solvents. So if you want to check the different solvents, you can check it. Otherwise, simple alone you can do it. Okay, so you have to firstly you have to do the reference sample. So in case you are doing the sample which is expecting, so this molecule is also I have did the quantum yield. It came around like more than 5. If your molecule is showing more quantum yield also, it will be like a dye. Okay, so it will be like a photo bleaching, everything it will be there. Okay, so everything it should be like a keep it good, and everything it should be good material. Okay, so what will happen, you have to my molecule is exiting around 360 nanometer. Okay, so your reference molecules also it should exit around like 360 only. So that material only you can take it as a reference. So for you just think what could I have chosen, what would have been chosen the sample for the reference. Okay, so which is which I have taken for the reference as the like what is quinine sulfate as the reference. Okay, so I have prepared 1 micromolar of the solution, so reference sample, as well as this one. As we know well about the like a quantum yield of like quinine sulfate, which is basically 0.52. Okay, so same sample we have to do the UV as well as like a fluorescence also we have to do. So in the fluorescence, what we can get it area under the curve. So you just go to the online, type it like a quantum yield calculator. So one first link it will become, so that you have to touch it. So there firstly it will ask the reference, like a reference, what is the quantum yield of reference. So that you have to put it. So if your molecule like some other compound, like your molecule is exiting around like 520. Okay, so for that you have to what you have to give rhodamine B or rhodamine 6G. So that it should be counting as the reference. Okay, so your sample and reference sample should have a same value of the excitation value. Then you can go for the quantum yield. Okay. So otherwise you can't do anything. Okay. So area of the integration it will ask. So area under the integration of your sample and reference sample also it could be possible by plotting in the origin itself. Okay. So those things you have to put, and the refractive index, and it will, one of the thing is the refractive index. In the refractive index you can get it in the online itself, like for water 1.80 for THF, like a 1.34 something, some values you can get it from the online also. So if you are putting those values in the calculation, you can get the quantum yield easily. So no need to do, no need to worry about it. Okay. So any other queries? Okay. So I'm just wind up this section. So I should thanks to Dr. Subhajit Hasra sir. He is my guide. So and this program coordinator, Dr. Chenna sir, Reddy sir, and Sasikumar sir, and cameraman. So I should thanks to them. Okay. So if any other queries also, you can message to the group. So I will be helpful for you. So thank you so much to all.